Hello students, welcome to the IMS Gate Academy. So in this session, we'll do revise on computer organization architecture. So I hope your preparation is going well. To boost your preparation, we do the quick revision on computer organization architecture. In this session, majorly we'll focus on the important observation from the each topic as well as the required formulas. So we will recollect them. So let's join the session so that so we can understand what are things are important from this topics of the COA. Okay, we'll start the session. Just confirm me that before starting the session, my voice is clear, all of you. Do respond everyone. Am I clearly audible? Fine. So now, looking into the session, the topics which I am going to be cover, like first initially we will focus more on floating point operations, floating point number representation, number representation. Okay, this is the first aspect we will see. The followed by memory organization, So from this memory organization, we will see the required formulas from memory hierarchy. First thing, then we look into main memory part, then third one cache memory, cache address mappings, and fourth one even secondary memory part also we will observe here only. Secondary memory, that is a physical structure of the secondary memory, especially we will take the consideration of the hard disk. So the third aspects we will see instruction set architecture and instruction pipelining. The fourth aspects we will observe I/O organization. From this the special focus on DMA controller. This is important. Fine. So these are the major topics from which we will see important statements, important formulas. We will try to revise them. Okay. So now the first aspects we will see data representation. From this data representation, so this data representation goes, especially so numeric representation. If you see the integer representation, one is what? Fixed point. One is the fixed point number representation. Fixed point number representation followed by floating point number representation, Okay. So this topic like fixed point part you might have studied from digital logic design, like you understand various number representation, their conversions, the various codes also you might have learned. So I am not going to focus those all the things. The things which are essential to be understand the floating point part we will also see from fixed point area. Okay. So look at the point from fixed point. First aspects if we see the fixed point. Okay. So fixed point number representation, right. So this fixed point number representation can be like one is integer, the second part is what? Fraction, right. Okay. Why it is called fixed point? Why the number is called fixed point? Radix point is fixed. For the integer, radix point is fixed what? Rightmost right or after LSB. For the fraction, the radix position is fixed before MSB, this MSB position before MSB. So now point is fixed, right? Both the case point is fixed. That is the reason fixed point numbers. Floating point number means what? The radix position is moving across the digit. It is a combination of integer and fraction, both part will be there. The position is not fixed, it is moving across the digit. That is what floating point numbers we can say. Okay. So any number if you take, so fixed point part I am talking, right, fixed point. From this one you see So from this fixed point, any number, either integer or fraction, if you take, let's take I'm considering as let n bit, okay, n bit number, binary number represents fixed point, like unsigned integer I am taking. First unsigned part will take. It can be signed and unsigned, right? The first, if I consider unsigned integer, let n bit number I am taking, next like bit 0, bit 1, bit 2, like this, So bit n minus 1. This is a binary number, n bit binary number I consider. Any number if you take, there are two things will be there. One is the value expression will be there, value expression. The second one, the range. Range is going to be cover the minimum value to maximum value, So what is the value expression will give? Sum of what weight of a system, sum of bits weight you can say. The especially I am considering as a binary number, sum of nothing but I am taking summation I equal to 0 to n minus 1, each bit bi multiply its power of I, like multiply its power, base of the system, Since base of the system binary, I am multiplying. This is a sum of the weights of a this number, right? Value expression. Now range, you understand range. So range is covering the minimum value to maximum value. What is the minimum value for this? When you substitute, every bit is 0. If every bit is 0, so that's 0, right? 2. Every bit is 1. Every bit is 1. What happens if you take summation value? This gives to 2 power of n minus 1. This you have to understand. I am giving a range of unsigned number 0 to 2 power of n minus 1. This is the important thing to be observed. Yes, I will address your question. Sir, I have doubt regarding memory. When the CPU generates the logical address, is the data checked in cache first or TLB? If the system uses a cache, TLB, page table together. We will address when we will take up the memory point of view. When we start discussing the cache memory time, we will address it. We will try to address that one. We will try to address that query. Better because we will go with the flow. So now little we will focus on the floating point, the fixed point and floating point. After that we will move for memory area. So we can observe those things also. Definitely we will observe it because we will mix a few topics from operating system as well as computer architecture point, so that you will understand better way. Okay. Just take if n bit number representing fixed point, unsigned integer, it has a range of 0 to 2 power of n minus 1, right? Yes or no? This is only correct? Yes or no? Now, so what are the other things to be observed? The second point you have to observe it. N bit binary number, n bit binary number representing fixed point, unsigned fraction part, I am taking, unsigned fraction I am taking, fixed point, unsigned fraction. Okay. So now that number if I take it like now fraction parts, right? A1, A2, A3 till AN, base of the system is 2. Similarly, I am telling first one is the value expression. Value expression is sum of all digits will start with 1. So till n bit, each bit should be divided by base of the system. I am writing like this. The second one, the range. So range of this number will be when all bits are 0, so 0 2. When all bits are 1, if you take the summation, this value will give 1 minus 2 power of minus n. This is important thing to be noticed. Yes, I hope this is correct. All of you do respond. 0 to 1 minus 2 power of minus n. This is 0 to 2 power n minus 1. This is two important thing to be observed, right? Because I am going each case wise. So you know this number. Yes, two things to be observed. Now third one to be understand. Third one, let n bit binary number, let n bit binary number represents fixed point signed integer I am taking, signed integer. Unsigned part over, signed part will take, signed part. So, I am taking the bit n bit number B0, B1, B2 like this, Bn minus 1 and Bn minus 2. This is a number. Okay. Signed means sign of a number will represent here. Here you understand MSB bit, this is the MSB bit, right? MSB bit. This is what? LSB bit, least significant bit position. This MSB bit Bn minus 1 I am taking, Bn minus 1. If this value is 0, 1, 0 indicates sign as positive sign. This 1 is there, this negative sign. This is an important thing to notice. Am I right? Am I right, all of you? This MSB bit is 0, the positive number, positive sign. MSB bit is 1, it is a negative sign of a number, but we represent sign. For representing this, you understand, for representing sign integers, we have a 3 notations you might have studied. Can you tell me, all of you, what are the 3 notations we have representing the signed integer numbers? Representing the signed integer numbers. Some of you tell me, what are those? One is sign magnitude, is it not? Sign magnitude. Second one is the 1's complement, and third one is a 2's complement notation. These are all notations. Complement. Okay. There are 3 notations we have for representation of signed integers. One is sign magnitude, 1's complement, 2's complement. I hope you understand. So, little differentiation I will give it. So, now in this case also we will observe representation and value expression range, that is it. 3 things we will cover, we will move for floating point part. Clear? So, I will be taking the point here. Okay. Suppose any decimal number is there, decimal number, any decimal number, and how we can represent in sign magnitude, how we can represent 1's complement, how we can represent it 2's complement. These are the 3 things need to be observed. Small values I will take, very small values to observe it. Okay. Look this all of it. Suppose I am taking as first 0 plus 1 plus 2 plus 3 and plus 4. Minus 0, minus 1, minus 2, minus 3, minus 4. So that we can differentiate it, all of them. One important thing you might have studied also, understand. For all positive sign number representation, in all 3 notations same, no difference. For all positive sign, it will be same only. Let us take 4-bit number I am considering. So, now 4-bit number 0, 0, 0, this also 0, 0, 0, 0, 0, 0, 0, 0. And second one is 0, 0, 0, 1. Why? Plus, this is sign, first bit is sign, right? So, sign 0, remaining magnitude. So, 0, 0, 0, no change in all the cases. For all positive number, no change, no change. No change for the positive numbers, all of you understand. Plus 3, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Plus 4, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, right. So, no change for the all positive numbers. I hope you understand everybody. When it comes to this negative number, and all 3 notations have different representation. Minus 0, how sign magnitude says, sign magnitude minus 0, negative sign. So, negative means negative how to represent. So, negative how to represent 1, remaining magnitude 0, 0, 0. Now, see 1's complement, simple thing to understand, keep it sign as it is, remaining magnitude invert it, this becomes 1, 1, 1. Now, see whatever you obtain from 1's complement, add 1, 1, 1, 1, 1 plus 1. 1 plus 1, 2, 0 sum 1 carry, 0 sum 1 carry, 0 sum 1 carry, 0 sum 1 carry. So, one thing you need to notice, this is ignored in case of 2's complement arithmetic operation, because we perform arithmetic operation of 2's complement representation, right. Whenever you get a carry, ignore it, it will not affect on a results. See why we got 0? Still you are representing 0 only, right. That is the reason you got a 0. 0, 0, 0, 0, right. Next one, minus 1. So, minus 1 means what? Minus means 1. 1 means what I would write? 0, 0, 1. Sign and magnitude. This one I said, keep sign as it is, invert the bits. This becomes what? This becomes 1, 1, 0. and whatever you obtain ones complement plus 1, 1, 1, 1, 1. Now the minus 2, minus this is 2, inverted keep it 1, 1, 0, 1. This becomes 1, 1, 1, 0. Am I right? Yes. Minus 3, 1, 0, 1, 1. This is 1, 1, 0, 0. This value is 1, 1, 0, 1. Minus 4, 1, 1, 0, 0. 1 I am keeping 0, 1, 1. This becomes 1, 1, 0, 0. So, this is a representation of a 3 notations: decimal, sign magnitude, ones complement, twos complement. Few important thing to be observed. Few and important. What? So, I want to know which is better to represent, better way to represent, which is giving the better, like you understand, giving the more storage thing among 3. So, one thing we can notice here. So, plus 0, how it is represented? All zeros. Plus 0, minus 0 separately. Plus 0 and minus 0 separately. Here is no plus 0, minus 0 represented same only, right? Minus 0 plus 0 same only. Suppose if I ask a minus 0, a plus 0, it won't affect, right? A only. But these two notations are separately representing. It is representing same pattern. 0, minus 0, plus 0 representing as same way only. So, in this case, in this range, we have a more, one extra negative number will be there, meaning 2's complement covering more range compared to 1's and sign magnitude. And 2's complement not require correction for the carry can be ignored. Hence, for the arithmetic operations, 2's complement is better than sign magnitude 1's complement. In terms of storage, it is covering more range than these two mechanisms. So, in practice, for representation of the signed numbers, we prefer 2's complement among these 3 methods. These are the observations. I hope this is clear. Is it clear, right, everyone? Everyone, is it clear? Now see. So, further thing we will observe it. What is the further observation? We will do it. The further observation is, we will take the value representation and range also. So, I am taking the notation, first thing, notation, okay, next. So, notations, 3 notation, value expression and range. So, range. So, 3 things need to be observed here. 3 things need to be observed. Okay. The first one, sign magnitude. Okay, what is the value expression? So, we have taken n bit number 0 to n minus 1, MSB bit representing the sign magnitude, like the sign of a number, right? This, in case of sign magnitude, sign bit will not participate in the computation. So, now value expression going to happen, sum of I equal to 0 to till n minus 2 only. So, like I am taking bi, right, bit bi, each bi you have to multiply 2 power of I. Now, this you have to understand. Now, here like n minus 1, last bit is bn minus 1. If it is 0, positive, if it is 1, negative, that is it. This bit is not participating, I mentioned, no, clearly I mentioned. This bit is, this is what MSB bit, right, MSB bit, right. The bit will not participate in case of sign magnitude notation, only representing the sign number. That is the reason it won't be under computation. So, only represent 0 or this one. When it comes to 1's complement, so 1's complement do not have no value expression. Reasons are because it is obtained by negating the sign magnitude value only. So, no value expression. Third one is what, 2's complement. So, 2's complement has a value expression. Complement. 2's complement has a value expression. So, now one important thing to be noticed here. Sign magnitude, 1's complement, 2's complement uses same hardware for arithmetic operations, and sign magnitude requires separate hardware required. Amongst 1's and 2's complement is performs better because not required any extra correction for when carry occur, simply we can ignore it. One other property of 2's complement, sign magnitude, like sign bit will be there in 2's complement, right, that will be participate in the computation. When you evaluate the value, it will be available, it is included in the value expression, but having the negative weight. 2's complement representation, sign bit as a negative weight. So, now I am writing the value expression. First I will take from all positive, I equal to 0 to n minus 2, each bit bi, you have to multiply its weight, plus, so last bit is there, what is last bit? B n minus 1 into 2 power of n minus 1. This has a negative, this has a negative weight. This is the value expression. Now, when it comes to range, range means what? This signed integer representations represent sign numbers as well as positive sign, negative sign as well as positive sign, right? So, same n bit number range 0 to 2 power n minus 1 is there, right? I have to give half of the space for negative side, half for the positive side. Then my range is going to be, so minus 2 power of n minus 1 minus 1 2 plus 2 power of n minus 1 minus 1, half of I given. Similarly, this range also same only, 2 power of n minus 1 minus 1 2 plus 2 power of n minus 1 minus 1. When it comes to 2's complement range, 2 power n minus 2 plus 2 power n minus 1 minus 1 only, here minus 1 won't be there. Do you know the reason why minus 1 is not there? Any one of you? Kindly comment it. Why we are not subtracting minus 1 in case of 2's complement notation, the range? Since it has only one pattern for 0, right? Minus 0 plus 0 represented as a 0 only. So, negative portion side, one extra negative number you can store. That is the reason minus 1 won't be there. That is what I said, it is covering more range than this two. One bit, one digit extra it will represent. Who? 2's complement, that is advantage. Is it clear, right? So, these are the observation. Based on this, questions couple of times asked in a gate paper. Ranges you should be observed properly. Every one of you understand. The revision session is much important, because you are quickly revising entire subject and understanding the various important formulas and important statements. So, now one more question we can expect from this area. Happen every, like most of the year gate papers if you observe, they asked, so like ranges of a given number among these notations. This is the one thing to be observed here. Other type of questions we can expect here, two types of questions we can expect. One thing they will give the decimal value, negative decimal value they will give it, and they will ask to convert into either sign magnitude and either 1's complement and either 2's complement notations, like this representation they will ask, decimal to this one, or sometimes 2's complement binary number they will give it, 2's complement binary number they will ask the decimal value. These are two types of questions, so frequently we can see in a gate paper. You might have practiced also. If not done, some problems you take up and practices. Suppose they will give one decimal number. Let us take example. Example, if I see minus 12 is there, is a decimal number. They ask us to represent sign magnitude, 1's complement and 2's complement. If it is a sign magnitude, what I said you, sign as it is you write 1 sign magnitude. Magnitude 12 nothing but 1 1 0 0. If it is a 1's complement, keep sign bit as it is 0 0 1 1. 2's complement nothing but what? You add 1 plus, right? If I add, what happen? 1 0 1 0 0 will come. This is 2's complement. So, now second case they can give this one, they can ask you reverse process you do, or otherwise you can apply some most shortcut method. What is shortcut method? So, this directly I can write in 2's complement. Minus 12 directly we can write in 2's complement. How we can write it? Looking at the weight, binary, so the bit position weight. First bit weight is how much will be there? 2 power of 0 means 1. This is 2, 4, 8, 16. See, you write the power more than, greater than next position. After 12, next position is what? 16 only. If I flat it, this, if I make it this position is high, 16 weight will come. Under 2's complement representation, sign bit has a negative weight. So, minus 16 comes, but we need minus 12 only. How much I need to subtract? 4. So, like this 0 0 0, you see 1 0 1 1 only. Directly we can write the given binary number, given negative binary number into what? 2's complement representation. Same concept you can apply when you want to obtain from given 2's complement number to decimal number. Means suppose example, if they are given like this, another example you can expect. They say the following number, okay, the following number, okay, following number is in 2's complement notation or representation is there, representation is there, like the given. Suppose one example 1011 is given, example 2 111101 is their assumption. Third example, if you take 111 3 ones 4 ones 1011 is there, like this given. How to take this value? What is the decimal value of it? I said simply 1011 is there, right? Take the power, evaluate the powers, like no value, position values. The value is 1, this is 2, 4, 8. But this is not simple 8, minus 8. Why? In 2's, these numbers are already in 2's complement notation, right? They are asking decimal value. So this has a negative weight. So now this value is minus 8 plus 3 equal to minus 5. That's it. This number how can do it? Now see same weights 11101. This weight is 1, this is 2, 4, 8, 16. Which is 16? Minus 16 plus 8 plus 4 plus 1. So minus, so what is the value total? Minus, so minus 3 only, right? Is it not minus 3? Minus 3 or not? So one more thing we can observe it. When such continuous ones are there, so you have to understand, not required to evaluate every bit. Suppose every bit not required to evaluate it. So now when number is 2's complement, first bit is like 1. You have to understand there is a sign bit only, right? Negative number only. So second bit also 1, meaning this bit is copied from here, this bit is copied from here, this bit is copied from here, this bit is copied from here. Your original number is 1011 only. Sir, how to understand means, whenever smaller number you are placing in larger register, sign bit might be simply copied only. When small number you place in larger register, so now how can I extend? So by copying the sign bit only remaining positions. So there is no, like if I remove this all ones, it will not affect on sign of a number or value of a number. Simply you can evaluate. This value is 1, 2, 4, 8. So minus 8 plus 3 almost minus 5 only. Minus 5. If you evaluate every bit position, if you evaluate, you will get minus 5 only. And I removing this, taking the original number, finding this also will get minus 5 only. So up to you can identify, because if I do it like this, number of arithmetic operations you can be reduced. This is the observation. I hope you understand this one more. So these are two types of questions we can expect. Chalo, we'll move on to floating point number representation. Okay, floating point number representation. So in this what you have to understand majorly, IEEE 754 standard is given. Standard is there. Standard for floating point number representation. This IEEE 2 standards will be there. One is single precision. My first one. Second one is a double precision. Getting my point? Single precision is the size is 32 bit length. Double precision size is 64 bit length. But gate is focused on majorly single precision only. From all the past previous year papers if you take, they have been framing on like 32 bit only, like. So then did not mention about double precision. Okay. So now let's see both the format also, no problem. Both the format will observe it. And before addressing some conventional approach was there before 1985. So after 1985 only they are given, IEEE given the standard for representing the floating point number. Before, every architecture used to maintain their own structure for the floating point number representations. Like Mantissa exponent form only, but bias value and exponent field, Mantissa field used to differentiate between the architectures. But after 1985, when the IEEE institution has given a standard, so every architecture has to follow same standard. Advantage of this standard is easily portable. So program code can be portable across the architecture easily. That's the only advantage we can obtain. Now look at this differentiation under 32 bit. What happens here? Okay, this 32 bit, so three things we have to observe. One is sign bit, exponent and mantissa, right? Sign bit is 1, exponent 8-bit fixed, this mantissa is 23, right? Yes or no? So, one thing we need to notice here, bias is how much, bias value, excess value how much here, how much value. So, look at this E, what E represents? Exponent. 8-bit, what is the range I can expect? So, 0 to 255, is it not? 8-bit range is, yes or no? Now, E equal to this 0 and 255. These two are special values, special values, reserved for special values. We cannot use these two numbers for representation of the normal numbers. So, now after removal of this one, capital E is available from 1 to 254 only, is it not? This is only available. And also we discussed, we have learned, we won't store as a given mantissa exponent as it is. We have to store in terms of bias form, right? Bias form. So, how we store the capital A, right? Capital A. Capital A is nothing but small e plus bias, small e plus bias. This we know, this important thing, right? For this original exponent, this is original exponent, right? Is the original exponent. Further some excess value I will add, then E value I will storage. How much maximum E can come? 254. Maximum, after adding this value, maximum this single precision can be represented 254 only. Minimum 1. Suppose case number 1 if I take. Case number 1, E as a maximum I am taking, E as a maximum. How much? 254, right? Yes or no? Now see. So, E plus bias is there, E plus bias is there. How much of E value, how much bias we should fix it? As per the learning, so bias value we should fix it. So, now simply 254, right? 254, half of you do it. So, 127 plus 127. Now, understand. So, maximum exponent which you can store in this register will be 254. In this original exponent should come maximum 128. Bias how much maximum you can add? 127 only. So, now bias value is fixed, this is important, bias is fixed now. So, in this case I can write here the bias is fixed, bias or excess value will be 127 is fixed here based on this point. Case number 1, right? Case number 2. Case number 2, E is minimum. How much E can be minimum? 1 only, right? 1. Now, E plus bias, E plus bias, bias is 127 fixed, right? What should be E should come, capital E. To get 1, how much I should subtract? Minus 126 should be subtracted. So, with this point, capital E range is 1 to 254, small e original exponent can come minus 126 to plus 127, yes or no? Now, from this user can end minimum minus 2 power of 126 to 2 power of 127. So, now understand, this smallest number can be representable, this largest number can be representable. Are you getting my point? Largest number can be representable. Sometimes they will ask question, they ask one of the paper, I guess, one of the paper they ask, one of the gate paper they ask, what is the positive smallest number can be representable in single precision format? That is nothing but this value only, is it not? 2 power minus 126 only representable. Now, they given the field in terms of mantissa exponent field given, you have to choose as per the options, but this only minimal, you have to understand. So, bias is fixed, this range is also fixed, right? So, now, so this is a major, the properties of a single precision 32-bit you understand, okay? This is a range, the special values, this is a combination maximum to get obtain maximum, this way splitting, minimum will be minus 1, maximum 127, this observation. Similarly, for 32, so 64 also, 64 bit means 1 bit for anyway sign, and mantissa have 11, remaining 52 bit for exponent, like mantissa will be there, exponent will be 11. The same concept can be applied. So, the distribution goes, special values 2 have to adjust and remaining thing can be distributed. So, that not required to discuss much, because we have to focus on majorly this one only. So, for problem solving you understand, for problem solving 2 important, so like I will give the 4 cases, 4 or 5 cases which are enough to solve all the floating point number representation under single precision. What are the 5 cases, sir? You observe the cases, all of you. So, I am taking sign bit, first is 1, right? Then this exponent has 8 bit and mantissa has 23 bits. and the value what this value representing will observe it. 5 cases I will be giving, just observe the 5 cases. Case number 1. Sign bit can be 0 or 1, yes or no? All of you do respond. Sign bit 0 or 1. This E value, if this E is 0 and M also completely 0, this is going to represent plus or minus 0. So, traditional or conventional approach not able to represent the zeros. Now, IEEE 754 standard have a provision for representation of zeros. Case number 2, it can be 0 or 1. If E is full 255 and M is still 0, M is 0, understand. Now, this represent the plus or minus infinity. I said special cases, E is 0, 255, this special cases. Now, case number 3, sign bit can be 0 or 1. Now, E is between normal number, right, 1 to 254, normal number. N can be any combination, right, any combination, right. Now, this represents the implicit normalization. I will give the expression for this implicit normalization. Case number 4, sign bit 0 or 1. Now, you understand E, this E value, okay, E value exponent is 0 and mantissa is not equal to 0. This is a denormal number or fractional form, you can say. Fractional form or denormal number, but smallest number which you can represent it. Case number 5, some number cannot be represented. So, E is 255. Now, M equal to any combination, This not represents any number, not a number. Example, square root of minus 1, infinity by infinity, such things are undefined. So, now this says some patterns of mantissa exponent cannot be representable. Now, from these 5 cases, the questions you can solve it. So, from the past years, so now I am giving the expression, right. So, I will give the expression for this implicit normalization. Value expression. Value expression will be minus 1 whole power of S. Implicit means 1 point M base 2 into 2 power of capital E minus bias. Bias is fixed 127 only. Case number 1. Next, fractional or denormal number value expression will be minus 1 whole power of S, point fraction or M, you can write it, base 2 into 2 power of, okay. Minimum is how much? Minimum E 1. So, how much bias is possible? Minimum E is 1, right? Minimum E is 1, capital 1. So, this 127. 1 minus 127 minus 126. This is the expression. So, from these two only we can observe. This is important thing. Here are 2 types of questions. One is, first they will give a decimal value, they will ask us to represent in binary pattern of 2's complement representation. Second case number, they give a complete binary pattern 32-bit, they will ask the value expression. So, you split out the mantissa and exponent and substitute in the expression, you will get it. This way you can solve it now. So, from the gate point of view, so till now majority time case number 1, they ask represent the number in IEEE format. Second one, 2 floating point number given, let's say A and B, add it, what is summation, like this. Third case, A is a floating point number, B also, A by B, division. Fourth case, A multiplication B, like this. These are possible questions they have repeated from gate 2023, they asked what multiplication only, before division, before addition, subtraction, like this. But what to do, sir? Sir, now do we have arithmetic operations? Arithmetic operations is little complex on floating point number representation. What you can do, first you get the number in decimal, addition, then you again store it. Get the decimal, divide it, get the decimal, multiply it, again represent 2's complement only. Otherwise, sir, getting decimal value and multiplying takes time. They may give us some patterns. Need to be observed. In this case, multiplication will be long. So, what they given 23 paper, one of the multiplication keep on, if you like properly, if you start simplify and observe, you will get 1. 1 into B will be B only, right? So, B is the one of the option. Little modification. This kind of observations you have to do it, so that problem solving becomes easy. So, how they are following? Simply they will give a 2 types of things they will give here. First case now, One is they give a decimal number, they'll ask us to represent in IEEE single precision. Second case, what they'll give a single precision format of entire 32 binary, they'll ask decimal value. They can give two floating point number, they can perform some operations. These are the possible type of questions which we have observed from the previous year papers now. Fine. So I hope you understand these are the important things need to be noticed. The 5 cases are important. So implicit normalization, fractional form or given expression, that we need to follow. So these are the things we need to be focused on. So coming into number arithmetic, what we need to focus here? If you take addition, it will be there, right? Addition, okay. Second one is a subtraction, right? Subtraction. The third one is what? Multiplication. Multiplication. The fourth one is what? Division, right? Division. Division, okay. Now, they like very rare like giving a number and perform some operations, but instead of that they'll ask some questions here. They give two operations. When I perform addition, then whether it is overflow or not. Otherwise, what are the conditions I need to apply to check whether overflow present or not? These important things. So now these numbers can be two cases. One is unsigned, and other case is signed. Two things will be there now. Look this, unsigned addition, so multiplication, division which want to focus much, addition like addition, subtraction if you see. Unsigned addition, when two additions are if added, there is a overflow when increase, like when large numbers are added with a small bit size, overflow may occur. Overflow simply like if carry bit comes and you have to detect overflow, simply increase the next position you will get, so you can able to fix it that number. Only question comes here when signed problems only. Okay, look all of you, what is the point we got to observe here? Signed numbers can be represented either 1's complement sign magnitude or 2's complement format, correct or not, right? So one thing to be understand here is two different sign numbers if added, please understand, two different sign, positive and negative say. Two different sign numbers are added, so no overflow, is that no? No concept of overflow, am I right or not? When different signs are added, no overflow because value will be reduced. But the only question comes here when same signs are added, like same signs are added. So there is a may possible of may not overflow. Am I right? May overflow or may not overflow, right? May pass overflow, like a simply otherwise, may causes to overflow, is it not? When same signs are added, overflow can occur. Now there are two conditions will be there. Suppose if I use 1's and 2's complement notation for representing the number, how to detect the overflow? So one rule number 1, rule number 2. What is the rule number 1? Very simple, you understand. Rule number 1 is very simple. Rule number 1 saying that sign bits, okay, carry, we have a carry in bit, okay, carry in and carry, understand, carry out bit are not same, this result is overflow. Suppose in a sign bit position, carry in comes and carry out will be, if both are different, definitely overflow. Second rule is that same sign, okay, same sign numbers are added and there is result. So result is in opposite sign, important rule, opposite sign, then the result is the results in overflow. What is second rule? Suppose two positive numbers added, result is negative, indicate overflow. Two negative numbers added, result is positive, overflow. This way you can detect. Means what? Sign, suppose example, this saying that sign bits are the sign bits like this here, is opposite, result is opposite. Or case number 1, 1 added, something magnitude will be there here. The result part is this sign is negative, so opposite is there, indicate overflow. Either one of the rule you can do it for detecting the overflow. Many times they frame this property, but this is not required to apply if solving the problem. Simply what you can see, given size of the number, check it in one's complement with this bits what is the range, and get the decimal values. Look at the decimal values, some of the decimal value will be representable given number size or not. If it is representable, no overflow, otherwise overflow. Like this you can do it problem solving, or you can apply this mechanisms of these two rules also, we can do it. So, this is a major observation from this one. In case of sign magnitude, sir, here 1s and 2s complement given, but sign magnitude arithmetic if you do, how to detect the overflow for sign numbers? Very simple. If there is a carry under sign bit position, because in a sign magnitude, sign bit will not participate in the computation, right? If there is a carry under sign bit position, that directly indicate what overflow only. So, these are the observation you can do from this one. So, now chalo move to, so next memory part. Next we will see memory part. So, now it is important. Now, so Mrigank was asking some doubts, so that can be addressed also, that can be addressed in this chapter. Now, see, in a memory organization, major focus will first will go memory hierarchy, followed by something we will observe on main memory, okay, main memory. Followed by we will see cache memory, cache address mappings also, cache memory, cache address mapping schemes, and fourth one we will see all cache related over, then we will move on to secondary memory. We will move on to secondary memory plot. So, these are the major observations we have to do on memory hierarchy. Yes, ma. Some of you, whatever doubts are there, you can start, you can ask the question, so that can be addressed clearly. Yes, all of you. Okay. The first we will see memory hierarchy. Okay, memory hierarchy. Okay. So, memory hierarchy, what is the objective? Level by level connection, level by level connection. Yes, ma. I hope you understand. So, now, so ultimately I want to reduce average access time. So, how the connectivity will go? Either this or this will be. So, in this chapter, in this concept, in this subtopic from memory management, key point to be understand here, finding the average access time, considering 2-level memory system, 3-level memory system, 4-level memory system, either parallel connection or level by level connection, all the consideration we have to do it, finding average access time only. So, this important thing to be noticed here, like this only hierarchy, right? So, hierarchy which you can see, like many levels will be there. Let us take here is a cache memory, here is a main memory, right, main memory, and here is a disk, The gate point of view, this is only important, finding average access time. Okay, look all of you, finding the average access time. So, now how to get the average access time based on the connectivity. Let us take case number 1. Okay, case number 1. Case number 1 indicates parallel connection. Parallel connection nothing but CPU is connected to all the memories. Let us take first just 2-level memory system I am taking. 2-level memory system I am taking. Okay. The CPU is connected to 2 levels like this, understand, parallelly. This is maybe level 1, this is maybe level 2 like this, level 1 and level 2, right. So, both are connected. Now, both are, when both parallelly connected, searching will happen parallelly. With the respect this, what is average access time will be. So, I am maintaining if data is present, represent H1, iterate. If miss occur, like what happens, parallelly placed, when you search here, if it is available, it is given and this line is ignored, or if it is not available, you will continue to search it, like this will happen. So, now I am writing H1. If it is T1, let us take T1 is access time for this, T2 is access time here. If this is miss occur 1 minus H1, automatically data will come from H2 only. This is an important thing to be observe it. So, parallel connection, clear ma? Similarly, if I take 3 level, so T average access time going to be H1 T1 plus 1 minus H1. See, 3 level if I take it, 3 level memory system. When there is a miss in L1, you cannot guarantee level 2 compulsory will be there, because there is a level 3 also. So, I have to specify iterate iterate of level 2. If it is it, so how much time required? T2 time required, T2 time required. So, yes or no? Yes or no? This is important. Let me take directly. So, H2, T2. Case 3. If both the case miss occur, level 1, level 2, both the case miss occur, 1 minus H1, H2, then T3 will come. This is the expression. Parallel connection means all the memory systems are connected directly to the processor. Okay, this even extended for even n number of levels also. So, now this you have to understand. Case number 2. Case number 2 is what? Level by level connection, level by level connection. This is important thing, level by level connection. So, let us take in the 2 level memory system, 2 level memory system, okay. That is CPU is connected level by level. First, it is connected to level 1, this is connected to level 2, like this, understand. This is level 1 memory, this is level 2. So, level by level only connected, 2 level. Let us take access time, I am taking T1, this access time I am taking T2, like this. Meaning first address is placed in, address bus will search in level 1 first, will search in level 1. If it is, I will take a data and given to the processor. If miss occur, so I will go to main next level, I will read the data, first I will place here, then I will give to the what level processor. So, within this structure, T average access time will be, so I am maintaining what iterate is what H1. If it is it in level 1, I will spend T1 time, H1 T1, I am right all of it. If miss occur 1 minus H1 miss occur, first of all I will transfer the data from level 2 to level 1, the T2 plus T1 both will be there. So, this is the expression. So, this expression for level by level connection. This mathematically if I simplify it, so now T average access time equal to, so mathematically if you simplify you will get T1 plus directly 1 minus H1 and T2, this only simple. How we can read this one? In a level by level connection, compulsory first you have to search level 1, right? First compulsory you should search level 1, yes or no? Compulsory search level 1. T1 is compulsory required. If it is present level 1, no T2 required. If it is not present level 1, additionally T2 required. That's one additional T2 required. When this miss occur, also we can write T average equal to T1 plus miss rate of L1, 1 means level L1. So, T2 is nothing but miss penalty of L1 also can read it. What I can read? It latency of level 1 plus miss rate of L1, then miss penalty of L1. T2 is nothing but access time of level 2 only. Why required to access level 2? If there is a miss in L1, right, that is what we call miss penalty. You should be very careful with these terms. So, they will not say directly sometime access times of each memory, they say miss penalty, hit late, hit time, like this they use the words. You should be very clear about this one, clear? Hit time of L1 plus miss rate of L1, miss penalty of L1 we can read it. In a similar manner, if I write 3 level system, 3 level, T average access time, 3 level. So, simplified expression directly writing iterate of L1, if miss occur in L1, H1, 1 minus H1. So, what is needed? So, additional T2 required, so level miss penalty of L1 required, right. If miss occur in level L2 also 1 minus H1 into 1 minus H2, then penalty from where? T3, like this you can write it. So, now simply you can write T1 plus M1 T2 plus M1 M2 T3 also we can write it T average access time. This is the important thing to be observe it. What is M1? Miss rate of L1. What is M2? Miss rate of L2. First anyway I have to search level 1. If it is hit or miss. If it is hit, T1 only required. If it is miss, additional T2 required. Even level 2 also miss occur, additional T3 required. This T3 is a access time of level 3 or miss penalty of L2. This way you can read it. I hope this is clear. I hope this is clear. I hope this is clear. So, this important thing to be noticed here. So, case number 3, consideration of spatial locality. Sometime whenever miss occur in level 1, we are going reading from level 2. Instead of reading one word, we read like a block of words we'll read it. So, with this consideration if I do T average access time equal to T1 plus, when there is a miss in L1, miss rate of L1, miss penalty of L1 nothing but we have to read from level 2 to level 1, not one data, block of words. So, I have to write it like TB2 I will write it. What is the TB2? TB1 I will write. TB1 means block of words, time taken for block of words from level 2 to level 1 plus M1, M2, TB2 I will write it. What is the TB1 now here? TB1 equals, suppose n words I am transferring, n words into T2. What is TB2? Suppose m words are transferring into T3, like this you understand. This expression. So, when to use this expression? When they say spatial locality, okay, spatial locality, meaning when they say when there is a miss in L1, along with the required word, group of adjacent words are read or block of words are shifted. Now, why B have to multiply? Because T2 access time is one word access time. N words are moving right, Ni multiplied. M words are moving right, M multiplied. Suppose the bandwidth is block is given. Suppose bandwidth is given block, simply you can write it T2 only or T3 only can write. But suppose bus bandwidth if given one block size given, you can one time only can take it. If it is a word length is like bus size is one word, then you have to multiply M words, you have to multiply. This you have to carefully observe. These are the major expressions which you can observe from memory hierarchy. So, now coming into memory, main memory. From main memory point of view, like understand, you know right, memory, okay, this main memory also. So, main memory also majorly two classes will be there, right. One is random access memory, read only memory, or we called read and write memory. This is what read only memory we call, right. Yes or no? This random access memory again classified. One is DRAM, dynamic RAM, SRAM, static RAM. This static RAM is nothing but your cache memories only. Cache memory is nothing but constructed by SRAMs only. DRAM is nothing but all your main memories. Main memory only with the right. RAM we call that DDR2, DDR3 which you see in a computer. That's all dynamic RAMs only. This dynamic RAMs are binary information stored charge form. Charge in the capacitors, in a capacitor. Clear? SRAMs binary information stored in terms of flip-flops. That's what SRAMs are costly, and this is DRAMs are cheap compared to this one. It has more storage density, less the storage density. These are the observation we can do it. Okay. So, we are storing the binary information charge form, right. So, capacitor has a leakage property, means after some threshold time, what happens? Slowly information gets discharged. So, you are going to lose information. Now, frequently, periodically you have to refresh the RAM. Every cell of a RAM chip you have to refresh it. So, it is required additional time over it, but it is okay. The value is small, negligible small value only. Syllabus copy of for what, ma? Ramgiri? The syllabus copy of computer architecture. So, you are looking for gate syllabus for the computer architecture. Very simple statements are there, like 4-5 lines only. That's nothing but entire syllabus. See, you just go through this lecture. From initial onwards, I specified also what are the major topics will be there from this subject now. Okay. Now see, so now here is what is important. It has a charge has a leakage property, periodically you refresh it. In a gate point of view, carefully they will make a question here. They ask like how much percentage time you spend for refresh operation, this one type of question. Or I spend this much amount of refresh operation, then how much time is available for read and write operation. Generally what we do, sir, how we know after some period of time only you have to refresh the RAM chip. So whenever we perform a read and write operation over the RAM, before performing the read or write operation, first you have to refresh it. After refreshing, you start read or write operation. So read and refreshing may take small time only. First you spend on refreshment, then you perform the read and write operation. During read and write operation, the ideal only, you cannot perform any other, during refresh cycle, during refresh period of time, you cannot perform read and write operation. You have to wait for some time. Then data is available, you can read and write it. This one aspect of the question. Other aspect of the question will be memory expansion. I want to construct this much large size main memory. How many memory chips required? What is size of the decoder required? So these types of questions will be there. Carefully we have to observe it, carefully solve it. So major focus from main memory RAM will be two type of questions. One is memory expansion, construction of the large memory size by using small memory chips. So divide it, you will get the number of chips as per the arrangement. So you have to see like how many RAMs you have to keep it vertical, horizontal, that properly you observe it, then you can do the arrangement. And other thing is what? Refreshment, like they will give the configuration, you see how many rows and columns, because RAMs mostly practice they implemented into 2-dimensional array form only. Now rows and columns wise there, from given data properly observe how many rows are there in each chip, how many chips are there, how much time required for to refresh. So these types of questions will be there, carefully you should answer it now. This is all about main memory. Okay. So I hope you understand the point. Now another important topic from computer architecture is cache memory. Cache memory. Understand. Here is a majorly the gate questions asked here. Cache address mapping schemes, cache design part only they will ask. Okay. So that will focus properly. Okay. First of all, if you understand cache memory, what is the cache memory? Cache is the smallest, right? Smallest. And it is the fastest also. Okay, fastest memory component in the memory hierarchy. Okay. And this cache maintains the one important thing, locality of reference. This is important things. Reference. Locality of references it maintains. What is the locality of reference? Locality of reference may confined as a function or some portion of the code. This is a memory, right? This program, entire program is here. Locality of reference, this locality of a code frequently, like repeatedly accessed by the processor. That's part of the program we call locality of reference. Okay. So what major content will be there in a cache memory? Nothing but the program data and instructions which are accessed by the processor so frequently. That is nothing but locality of reference. This locality of reference can be two things. One is temporal locality. Second one is the spatial locality. Okay. Temporal nothing but with a different time, same data element being accessed by the process several times. For loop is there. In a for loop, suppose you mention x equal to x plus I, only one X element repeating 100 times assumption, 100 times incrementing. One element I am reading 100 times incrementing. Same element are accessed by the process several times with the different times, several times access, like I equal 0, I equal to 1, I equal like this. That's we call temporal, time. Spatial thing nothing but you understand. When you access one element, it is likely, likely to be accessed adjacent element by the processor in the future. Meaning, what spatial locality suggests that whenever any array element being accessed by the processor, it is likely to be accessed next addresses or not. Next element, next adjacent addresses will access by the processor or not. So it is suggesting that whenever you are placing some item, one item in the next level memory, like top level memory, along with the referred data, some adjacent words also, group of words or block of words you keep into next level memory. In the future, processor may be refer that area so that it will be available in the cache memory only. It will reduce the future penalty. That is what spatial locality. Sometime match the following statement comes, you should be aware of this statements. They should be aware of statement. One is locality of a reference thing, this comes under two types will be there. Now one more, principles of locality will be there. From operating system point of view, working set window, working set model maintain the principles of locality. Same, meaning is same. Some set of pages frequently referred by the processor, that we call principles of locality. Talking about working set model, this is what? Locality of reference for the cache memory. This differentiation you should be observed. Fine. So now coming to more important point. Here cache address mapping schemes we are going to observe. Cache address mappings. Address mapping schemes. Cache address mapping scheme. Why cache address mapping schemes required? In the memory hierarchy if you see, top level memory is the cache memory, next is what? Main memory, and bottom memory if you take disk, right, disk. Look, all of data will move from disk to memory in terms of pages or segments like wise. By the operating system will take this transmission, correct or not? Operating system will take transmission data between main memory to disk. From main memory to cache memory, data will move in terms of blocks. This taken care by the hardware control unit only. No involvement of the operating system. Now, large size of this main memory, how we can map to small size of cache memory, because cache size is smaller than main memory. Large size of the disk if we map to small size of main memory by the operating system. Similarly, this we have to map, address mapping from where? Main memory to cache memory. Cache address mapping converts from main memory address to cache address. So there are three schemes are there. One is direct address mapping. Second one is what? Full associative. Third one is set associative. Simply or associative also can call this one. Simply you can call associative, either full associative or associative. Third one is set associative. Three mapping schemes are there. You might have studied. So in a tabular form, like in a columns and rows wise, we'll observe all the important things related to three mapping schemes here. Fine, ma? So now we'll see what we do. All the cases we'll observe it. Okay, now see. First one mapping schemes I am taking here. I will take it. Here is a mapping schemes, right? One is first one direct address mapping. This is very, very important. Address mapping. This is very, very important things. Individual you might have studied, but we'll see this one. Direct address, let me write here. Associative. Third one is a set associative. In this example, I am taking as a K-way set association I am considering. Okay. So various things we'll observe it. First thing is physical address is there. Okay, physical address. What we do in this example, okay, processor CPU will generate the effective address, right? Effective address nothing but virtual address or logical address, which is containing with various addressing mode involved. It generates the address. So that address we convert into physical address by help of page table from operating system point of view. Or I can use a TLB or page table, I'll get the physical address. Once I'll get the physical address, this address generally given to main memory to access only. It is given address to main memory only, correct or not? In middle, cache controller will capture that physical address and searching into cache memory by applying various methods. Then if you get a block, from that block will read a block data given to the processor behalf of the main memory. Processor completely not aware of existence of the cache memory. It won't ask the data for cache memory, it will ask the main memory only, because from CPU point of view, main memory only important. But to optimize the time, we kept the cache memory, right? Middle will take and split out this physical address into how many parts here. The physical address is split into three things, you understand clearly. One is tag, first thing. Next is block offset or block number or line number we call. This is word offset. You understand? Word offset indicate the how many bits we could address a block, word in a block. It is depends on the block size. Carefully use my words and note of it. Word offset values are depends on the block size. Block offset value depends on the number of blocks in the cache memory or number of lines in the cache memory. Tag bits represent which block of main memory present in the cache memory. Are you getting my point? Because the gate people ask this value, so they'll ask it. They'll give a physical address. Physical address with respect to main memory size only. If I know physical address, I can get size of the main memory in terms of bytes or words. Clear? So this is the division, and dependency what? This depends on the block size, depends on the number of blocks in the cache memory, depends on what? How many main memory blocks are mapping into cache memory. That I can write m by n. If I take, so let me write later this tag values. Now here in this case of physical full associative, now understand here. Now understand. In case we are using the mapping function called k modulo s, we will use it. Here no mapping function is saying that you can place anywhere. Associative full says that main memory block you can place anywhere. So that we don't have index, only we have a tag plus word offset on nothing. Only two fields will be there. In this one physical address, we are dividing number of blocks into sets. So now hence we have a set offset and word offset will be there. Here the block offset, set offset will be there. Means number of blocks further we divided into sets here. Set offset depends on number of sets in the cache memory. Again word offset depends on block size only, right? This is a difference. Now second one. So what mapping functions we are using? Here mapping function we use what? K modulo n. What is the K? K is nothing but main memory block number, right? What is n? Number of blocks. So blocks in cache memory, this you understand, in cache memory. Now here is no, anywhere you can place it. What is what mapping function? Anywhere you can place it. Here is what? K modulo s. What is s? Number of sets. Number of sets in cache memory, right? In number of sets in cache memory. What is K? Main memory block number. Main memory block number mapped to anyone like this. Clear all of you. The third point. What is third point? We'll observe it. So third point we'll have to observe it. What is the observation? Third point here. How many comparators required? Comparators required. Understand, this is important point. So in this case what we do? We divide into blocks, right? Blocks we divided. So blocks and mapping function k modulo n. K modulo n giving only one position, right? One block only. In that block only we placed it. So we have to search only one block out of all. Only one block directly we are searching. So that one comparator is enough. In this case we place anywhere. You have to search all. Suppose n comparator required. N is what? Number of blocks are there. N comparator required. In this case what we do? Number of blocks grouped into set. mapping into set number. In a set you can place anywhere. Now in a set size you have to search. Say K is what? Set size. K comparator required, N comparator required, 1 comparator required. So hardware is costly, is it not? Hardware is costly. Now further same thing I am doing, like 1, 2, 3, right? Now suppose I am talking. So implementation cost, if you see, implementation cost, okay, it is simple. First one is simple because only 1 comparator required. It is costly. Why? Because n number of comparator required. It is a medium, moderate, you can say, moderate. Moderate. Now performance, if you observe, performance, okay, it is the slowest, it is the slowest mapping. Slow. Why slow, sir? Conflict penalty will be there, okay, due to slow, due to what? Due to more conflict penalty, more conflicts. Now it is very fast, very fast. It is a medium. Why fast, sir? Because no conflict. So no conflict here, less conflict. Conflict will be there, but less conflicts, because mapping scheme is there, right? Mapping scheme is there, right? So any other observation? Physical address division is there. Now other things. Fourth point. So it to time. How to measure the it to time? How much time required to say whether the word is present in the cache memory or not under 3 methods. So it to time or it latency, time for it equal to, first I have to access comparator will be there, time for multiplexer will be there, time for multiplexer plus time for comparators also will be there. Physical structure, if you see, if full associative, time for it, okay, equal to no multiplexers here. So now one is comparators, many comparators will be there, plus OR gate also we are using. Now time for it will be, here is multiplexer will be, because there are many sets, you will select, right? Select one set, multiplexer. Within the set, you have to search all the things. So comparators also required, plus OR gate also there, time for it. So this is a one other observation. Physical address division, number of comparators, mapping function, implementation cost, time for it. So these are the major thing to be observed here, Okay, one note point we can see. So one note point we can see. Okay, note. What is the note? I given, right? One is a block offset. Block offset depends on number of blocks in cache memory, where n equal to what? Number of blocks in cache. So now word offset depends on what? Log of block size. This is base 2. And set offset depends on number of sets. Log of base 2. What is the S? S equal to number of sets in cache memory. Tag bits equal to log of m by n. Sorry, I'll write properly. M by n. For it is a direct mapped. So this tag bits equal to, directly I can evaluate, log of m by s, number of sets. If you divide also you will get. In case of what? Set associative. Because those many blocks you map to that set, right? You have to divide by sets. Those many, that block you are mapping to number of blocks, right? M by n. So these are the main observations we can do it. Fine. So I hope you understand the points which I discussed about 3 mapping schemes. Okay. So these are the main important. Based on this only you can able to answer the questions. So one question I am taking here. Look this, one important question. One question you can see, all of you. What the question says? Consider p-way set associative cache with 16 into p blocks are there. Assume that main memory also has same number of blocks in as cache. Number of blocks in cache, number of blocks in main memory will be same only mentioned. What is the tag size in this organization? They are asking. Tag. So tag bits only they are asking, right? Tag bits only. Tag. See now tag under set associative. So tag bits how to find in this case? M by S only, right? What is the M? So it's direct formula. So M by S only base to write. Okay. M is what? Main memory blocks, right? Main memory. So number of blocks in. Number of blocks in main memory. Okay. Main memory, that is M. What they said, assume that main memory block also has same number of blocks. How many? 16 into P. Now, so now S value are found. Number of sets. Number of sets, S value. How to get the number of sets? Do you know? Number of cache blocks. So number of cache blocks divided by block size, nothing but set size. Set size nothing but K way set also, nothing but here use P way set, P only I have to do it. So number of blocks in cache in this question, how many they get? Consider a P way set associative cache with this many blocks are there. So 16 into P by P only, you will get 16. Okay. Set size sets we got 16. Now, can I substitute log base to M value how much? 16 into P by 16 only. 16 cancel. So log P base 2 is the answer. Yes, this only answer. Log P is answer. One of the option would be there, that log P is answer. This way we can able to solve it. The other questions you should practice because they give main memory size, they give a cache size, block size, number of blocks, sometimes directly number of sets. They'll ask tag size, tag bits, word offset, set offset, block offset. One more thing, important thing you notice, they can ask even tag memory means what? Tag metadata size also. Tag memory how to calculate? Because tag bits are associated for each block, right? Simply number of blocks in a cache multiply by tag bits you should multiply respective addressing mode. Respective address mapping scheme. That so what is scheme you use? Simply tag memory can be calculated, tag bits multiply by number of blocks only. That enough problems you might have practice. So these are the things to be observed here. Fine. Now one more thing to be understand here from this cache memory only. One is cache block replacement algorithm. Cache block replacements. It is like a page replacement algorithms only. You should study first in, first out, right? Now optimal, LRU, MRU like this. These are things to be focused. That's similar to like operating system point of view. You might have studied a page replacement algorithm. Same only. Concept is same only. I am changing. If the question is being framed from computer architecture, they say block replacement. If it is from operating system point of view, they say page replacement. That's no difference. Concept is same only. Fine, ma. This need to be observed. Apart from one more thing need to be focused here. Cache updation methods. Cache updation methods. Updation methods. Okay. So one drawback of the cache memory will be the data inconsistency or cache coherence problems we call. Data inconsistency or cache coherence problem. One is a major drawback of cache memory. What is that? So what is the cache data inconsistency? If you not update into main memory, okay, what happens? Same information will be different in each level. To solve such problems, you apply some proper updation methods so that all the memory levels same information should be there. Meaning suppose initially in a program there is a suppose one data element, let's take x equal 10 is there in a secondary memory. When I placed in main memory, that is x equal 10 only comes. When a CPU start reading the x value to modify, x value may be read 10, modify to 20. But it is only updated into cache memory, not reflected to main memory. What happens? Secondary memory x value 10, main memory x value 10, in cache memory x value 20. See, same information is supposed to have all the levels same only, right? But differently is there. To solve this problem, proper updation methods updation methods we can use to keep the data consistency across all the levels of the memory. So, we have two protocols, one is write through. So, write through protocol, write through updation or write through protocol, and second one is a write back protocol. This is important, mix of question they can ask, write back updation or protocol you can say, write back updation, write through updation, write back updation, through protocols are there, important because questions comes through memory hierarchy included with this one also they can ask. So, mix of this question they can frame it, we should be aware of it clearly, write through, write back. Okay. So, now concepts you might have know also, but let us see understand the concept and we will see the major expression formula, because they ask average access time, only read access time, write access time, mix of it, all the types of questions we can expect from this area. What is the first thing you will say? Write through protocol. Write through protocol says that simultaneous updation of cache and main memory, meaning whenever a processor, you understand, if you take first one, here is a CPU, right, here is a CPU, level 1, here is a level 2 memory is there, or else you take it, this is a cache memory, or else you take this is a main memory only, okay, main memory, okay. Now, connected what level by level connection done assumption. Some value something x equal to 10 is there, I place x equal to 10 and given to x equal to 10. If the value is modified to 20, immediately it is writing back to 20, also it is writing back to where 20, simultaneously updating both the memories in case of write through protocol. So, completely data inconsistency or cache coherence problems are avoided, because all the way same, the moment you update it, immediately in the next moment we update here, that is a point you should be understand here. Now, suppose cache access time is TC is there, main memory access time TM is there. If I ask for time for updation, how much time we require to update this operation equal to maximum of TC comma TM only, is it not? Why? Because simultaneously updating, obviously main memory takes more time, maximum of this two. So, obviously see it, cache access time less than M only, so answer will be TM only, is it not? So, otherwise if two different levels are there, if they not mention cache and main memory, simply you take maximum of this all memories, that is what simultaneous updation, whichever memory takes more time, that is a maximum time required to update the data. Clear this updation time? I hope you understand this point clearly. Okay. This is about write through protocol. Okay. Write through means I am reading when something is modified, I update all the way, I have to update it all the way. Now, second, so write back protocol, second is what? Write back. What is the write back? Write back updation says here. Okay. Now, with the write through, what is the advantage? Cache coherence problems are resolved. Over it is, you understand, if suppose I am running a instruction under for loop of 100, I am updating one value, incrementing 100 times assumption or 1000 times. Each updation will be reflected to memory access, correct or not? Now, memory overhead is like accessing memory will be more time than cache memory. Now, this time will increase or not? When number of updations are more, this method performs what? Worst I can say, or number of updations are less, this can give better performance. So, now write back saying that whatever updations you want to do it, you do for only cache memory only, meaning you understand this says that CPU connected is a cache memory, okay, cache memory, this is connected to main memory or some main memory, okay, main memory. Now, suppose some value read x equal to 10, so that I place x equal to 10 given to x equal to 10 here, okay. The value is modified to 20, only modify 20 here only, that is it. Suppose modify 30 only, modify to 100, just update here only. Like this, what are the values here? You have to update here only. At last, end of this program, final value you have to update into main memory, as well as you have to update it into secondary memory also. That done by the operating system. We won't worry about that one. That taken care by operating system. Clear? He is saying that you do only updations for cache, not for main memory only. At last you can do it here. Sir, middle, suppose the cache memory in terms of blocks will be there now. Sir, in middle, suppose during this execution, if this block is chosen for removal, then what to do, sir? That moment also you have to update. Very simple saying that main memory is updated when only when a concerned cache block is chosen for removal, a concerned cache block chosen for replacement. That time you have to update it. Sir, any one of the block is not at all chosen for replacement, sir. At last definitely you have to update here as well as secondary memory, right? In middle of time, any cache block chosen for removal, in that modified data is there, you have to write back. Sir, how to know, sir, this data is modified, block is modified or not? We have seen, we use one dirty bit here, we add dirty bit here. The dirty bit is 0, so data is not modified. If dirty bit is 1, at least one of the word or at least one instruction, one data element is modified in this block, so that you have to write back. So now whenever concerned block is chosen for replacement, that moment we will update, otherwise we won't update. But when you will update, at lastly I will update. Hence, in application required more number of updation, this protocol will perform better, but still cache coherence problem is not avoided, is it not? Because here is something data, here is something data only, but we are going to reduce what? Time only. Fine. So this is the main important thing to observe. So apart from here, there are two terms will be there. One is read allocate policy, second one is a write allocate policy. This is a very important thing now. Sometimes they use or sometimes may not use, indirectly they will say read allocate policy, write allocate policy. What is the read allocate policy, write allocate policy? Under this protocol, whenever we go for reading a data into cache memory, assumption reading, I am going to read for data. If the data is present, I will read and give into the processor. If read miss occur, I am going for reading, data is miss occur, I will go to secondary main memory and bring the data. Read allocate policy says that when read miss occur in the cache memory, when you go for reading a data from main memory, along with the referred word, bring block of words, one block of words bring place into cache memory. This implies future penalty going to be reduces. Are you clear? If I say no read allocate policy, nothing but we won't read it extra block, only we read it required data. What is the write allocate policy? Simply, I want write a data into cache memory, because every time we write a data in cache memory, not to main memory. But if it is miss occur here, I went for writing a data into cache memory, data is not there, my original essential data is not there, somebody replaced. Then when write miss occur, again you go for main memory for writing, right? You update, and along with this updated data and group of words, a block of words you bring into place in cache memory, future penalty will reduce. That's what write allocate policy. These two things need to be observed clearly. So with this consideration, so like three or four formulas will be there, we'll observe it. First, under write through updation considering first case number 1. So now one more thing to be understand, the CPU is performing operations, right? CPU operations, what are the operations will have? Either read or write only, right? Reading means what? I can read instruction or data. What is writing? Data writing only will be there, no writing of instruction, right? Instruction will fetch for execution only. Once execution, results will write back. Will write into cache or main memory, correct or not? Operations are read or write. Either read data or read instruction, write data. Three things will be there now. See, first thing, T average access time indicate any type of operation I performed on memory levels, how much average time required to perform one operation, either any operation, either read or write. So which include both read as well as write. So I am taking the frequency of read operation means how many read operations are there, followed by each read operation how much it will take, plus frequency of write operation, meaning indicates write percentage, multiply by average average write operation, this is the one thing, main formula, combining read and write. Now splitting out, second one, T average read only I am performing, read only, okay, read only, getting my point, read only. I want to read a data from level 1, level 2, level 3 or cache memory, main memory, like this. Any level it can come data. How much time required? How reading will happen? First I will go and read into cache memory. I should know iterate rate of read, right? So I am taking H or indication, iterate rate of read operation. Now TC I will take, TC is nothing but what? Cache access time. So when is it in cache memory, access it, right? We have studied level by level. If miss occur 1 minus R, so where to read? From main memory only. I am using read allocate policy is there. Already you spent TC amount of time, it miss occur. I have to read data from main memory. I am reading. If you read one word, simply I can write TM only. Simply I can write TM only. But when I allow read allocate policy, you have to bring what? Block of words, right? So time for block. So I am TB I am writing. So no confusion, right, all of you? So this is a expression, read. Now third expression is what? T average write operation, Where I will write? Under write through protocol, we are writing parallelly. Obviously updation time only, updation nothing but main memory access time only. But I want to include write allocate policy also. What is the write allocate policy says? So first I went for writing here into TC time writing, okay, writing nothing but, so now write nothing but T updation time only, right, T updation time, okay, means if it is the write hit, if it is a present in cache memory, you write it, anyway main memory also will write it, parallelly is happening. Suppose I went for cache memory to write, miss occur, it is not there, so 1 minus HW, so now see, so what happens, you have to update here, I allowed what? Write allocate policy means you have to bring the new block also, additional. If I am not bringing anything, simply updation, suppose you understand now. No write allocate policy is there, meaning when write miss occur cache memory, I am writing main memory, I am not bringing anything. So TB is not there. If TB if I ignore, then this expression if you simplify, can I get directly T updation time only? TB if I remove it, only T updation if I take it, mathematically simple T updation only, right? So directly could write T updation only. But why we read it? So write allocate policy also there. Suppose in a gate question they mention, when there is a read miss, write miss occur, I will bring a word of one block of words. That is a consideration. If I want to simplify this expression further, ignore this. Simply I can write T updation time only. Now I know read average write operation, read operation, I can put in this expression. Now T average access time will give to perform one operation among the memory systems. It can be read or write operation here. Under this mechanism, you should be carefully observe it. I hope this is clear. Okay. So another thing they can ask throughput also. The fourth point if I take throughput of the memory system if I ask. So direct expression, you know, T like 1 by T average access, that's it, 1 by this value only gives. So how many words will be transferred per unit of time is given by throughput only, fine. So next one, so write back updation if I use it, first expression will be same, no change, this frequency of read operations multiply by average read plus frequency of write operation multiply by T average write operation, right? This is read and write. Now if I take second expression as T average, okay, read. Now under the write through protocol, write back protocol, I want to read it. Similarly, so now iterate into like iterate of read from cache, if it is it occur, TC time required. If 1 minus read is there, I miss occur, observe carefully. If miss occur, I went to main memory. Now again read and write allocate policy is there, along with the word group of word, one block of words I brought. The block I want to place in cache memory. Suppose understand cache memory, cache is full assumption. What happens here? So read miss occur cache memory, went to main memory, I brought block, I want to place cache, cache is full. What to do? You have to remove one of them. Right? So I selected one block for removal, but that may be dirty, right? That maybe some data is modified or not. If it is a dirty, what you have to do? I have to write back. If it is not dirty, simply delete, new block can be placed or not. So I am taking D is a dirty rate. If it is a dirty, you have to write a block. So now old block will be there, you have to write back access time, and new block you have to bring, right? Yes or no? Plus TC time will be there. This is expression. Plus no dirty is there, sir. No dirty. Simply only new block I place, overhead of TC will be there. This is expression. So this part will be when block is dirty. This expression used when a block is clean, and right allocate policy is used. So this way you have to observe it, all of you. Everyone, I hope you understand, right? Chalo. The third one, third expression, what? This is a read operation. T average write. So write operation. First I am writing in TC. Every time we will write in TC cache memory only, right? Every time we write in cache memory only under this protocol, right? Suppose I went for writing cache memory, miss occur. 1 minus HW miss occur. Then what to do? I have to write in main memory. I written. Write allocate policy is allowed. I have to bring block. I brought a block. I want to place it. Cache is full. Then what to do? Again you have to remove or not. How to remove? I have to check for dirtiness. So D percentage is there. So TB old block write back, and you read the new block plus TC overhead. If there is no dirty, 1 minus D percentage into only TB new and TC will be there. This expression. You may think that, sir, both are same expression, answer will be same. No, because read percentage different, write percentage different. So now both will not give same answer. This carefully observe, the little confusing also. My point was why I added all the things. Right allocate policy is there. Sir, no right allocate policy is there, sir. Then how the expression will happen now? So when this miss occur, I am going to read from memory, second memory. Okay, I will bring one word only, one word I will bring it. So where to place, sir, that word? If that particular block present in the cache memory, you place. Otherwise, you have to remove one of them and you have to place it, right. Are you getting my point? Only one word I have to. I have word placing nothing but one of the block only you place. If block is present, you can place it. Block is not present. So again cache is full, you have to replacement to be done only. This is the observation. Now under this also throughput is asked 1 by T average. First you have to find this two, you will place it. So 2-3 times or 3 or 4 times I saw gate papers this part, some combining all also they asked. Some sub part of this expression asked several times in a gate paper. You should be able to answer it. Another type of question they can give, they give a program, they say row major order, column major order stored. How many its are there, how many miss are there? These types of questions also comes. Properly observe. You look at a row by row, how you are storing, how many blocks are there, how you are mapping, then how many, sometimes overlapping also they'll ask. This type of problems try to practice it so that you will be in a good position to answer it. Now coming into secondary memory. So this can be discussed last, but under memory part only we can observe. Here there are two things need to be addressed. First thing, this ask the disk size, they'll ask disk size. First question. How to calculate the disk size? Simply number of surfaces, okay, number of surfaces multiply by number of tracks per surface multiply by number of sector per track multiply by size of the sector. The simple thing you have to do it. Simple thing you have to do. Second question, so drive offset or they can ask number of bits equal to address a sector will be simply, so now simply I can say log of, okay, log of number of surfaces plus number of tracks plus number of sectors, that's it. Base 2 you do it. How many surfaces? Suppose 16 surfaces are there. 16 means 4 bits required. then how many this required? Suppose 1000 tracks are there, 10 bits required. Like this you understand, base to apply, you will get it simply. Or log s plus log t plus log sector, log this also, that also can write it. There is no harm. Or now better you can write it, log surfaces plus log of tracks base 2 plus log of sectors only, not sectors is not required to take, because you have to address the sector only. Third point is what? Average access time of unit is what? Sector only. Sector only. This is seek time plus average rotational latency plus data transfer time plus some controller overhead also. Sometime control overhead. This may be optional, or sometimes they given, you add it. Seek time they will give it, you need to find out average rotation latency, nothing but 1/2, like now you understand, 1/2 of rotation latency, one rotation latency find out off value, and data transfer time depends on the what disk rate, like rotation speed. This is important thing to be noticed. And fourth point here, DTR, data transfer rate, they will ask it, data transfer rate. What data transfer rate? One track, okay, one track capacity one track capacity by one rotation time, one rotational time. This is the important thing to notice. DTR means data transfer rate. This important thing to notice. 4. And the fifth point you understand, cylinder based question they will ask it. Cylinder based question they will ask it. One is logical address. Logical address would be like cylinder number, surface number, sector number will be there. Cylinder number, sector number, surface number will be there. For given a sector, linear sector, they will ask these values. How to get it simply? Xth sector is there, that you have to divide. Like let me write like. Okay, so cylinder based question, one question is a logical address for given a xth sector. Very simple to understand all of you. Xth sector is there, right? Okay. To get the cylinder number, 3 addresses, right? Triplet address. Cylinder number, this is a cylinder number. This is a surface number. This is sector number. Okay, now see. To get the cylinder number, I should divide by cylinder size. Cylinder size in terms of, I am taking like surfaces. M is what? Number of surfaces. This is number of sectors. Sectors per track or surface, you understand. So, suppose if you take, what is cylinder concept? Similar position tracks across all the surfaces, right? This is a cylinder. Now, similar position track nothing but what? Similar positions of surface, number of surface multiplied surface size, if you do the cylinder size, right? So, M into N divide, you will get cylinder number, right? Some remainder R1 you will get. This remainder R1, when you divide by, now I need surface number I need. So, surface number is surface size nothing but number of sectors. When you divide, you will get a surface number. Second remainder whatever you will get, this is nothing but sector number only. So, combiningly it is giving what? C, H, S will give triplet address, that's it. Now, second question, what is second question? They ask linear address, okay, address for a sector of given triplet address C, H, S. Sometimes they will give triplet address, they will ask linear address. This is very simple. Cylinder, you have to convert into sectors only. One cylinder size nothing but number of surface into number of sectors per surface plus surface size N into this H value, surface number into number plus S. M is nothing but, what is M? Number of surfaces. what is n value? Number of sectors per surface or track, or sectors per track, same meaning is same only, you multiply. Sorry. So this is the understanding about this thing. So majorly, so this to be covered from disk point of view, easy things only, either size or offset value and access time, or in terms of DTR sometimes they ask, cylinder trick question they can ask it. These are the thing to be observed it. These are thing to be observed. Now third chapter is very much important. Third chapter is very much important. So we'll observe clearly. Okay. So before addressing, we'll take a little 2 minutes break. So now look at this instruction set architecture and instruction pipeline. From instruction set architecture, here is looking at instruction format and addressing modes, various addressing modes need to be observed clearly. Okay. Instruction format nothing but you might have studied 3 address instruction. Second one is a 2 address instruction format you observe, and third one is a 1 address instruction, and the fourth one is a 0 address instruction or stack organized computers also can tell. So this we call general register CPU organization. This is what accumulator based architecture we can tell, right? 3 things, 1, 2, 3 like this. Majorly this can be used in RISC type of architectures use it. So all combination can have CISC can have anything, but RISC is supporting either 2 or 3. From this one, gate will be focused instruction encoding nothing but they say this many instructions are there, this instruction format, it will support 2 address, 3 address, 1 address. Now they give among 2 set of instructions they will give it. They will ask how many 1 address can be formulated, 2 address can be formulated, 3 address can be formulated. This type of questions will asked. We should be carefully answer it, this one, fine. So that will observe here, that type of question they can ask it. Okay, from this the architectures only, fine. Now suppose they given like this assumption. This is having a, let's take 32-bit instruction is their assumption, and 8 address bits are there. 8 address bits. This 8 address would be memory or maybe register also. Even memory register also can have. Now this architecture is supporting assumption assumption like 1 address as well as 2 address and 3 address is supporting. 1 address, 2 address, 3 address also supporting. Now 1 address, this one, right? So 2 address, nothing but how to make it 2 addresses. So 1 address as is already will be there. Now 8-bit from opcode, like opcode field, how much will be now? Opcode field be going to be 24, right? 24 only. 24, right? From this opcode 8-bit you need to borrow, you have to take it or not. 8-bit you are taking nothing but 2 power 8 instruction from 1 address instructions are removed or not. So 8-bit already there, this many 2 power 24 instructions possible for 1 address. In order to support 2 address instruction, 2 power of 8 instructions are taken to this one. That will be less. Now this opcode field will be, how many will be there? 16 only. 16 only. So 24 plus 8, 36 only, 32 only, correct or not? Yes. Now 8, 16, 16 will be there now. Now if I make it a 3 address instruction, nothing but 3 will be go, 8, 8, 8 will go. So opcodes how many possible? How many possible? 8 only is possible here. Now with this respect, now we have borrowed here, right? So with this respect, I am going to give a formula. I am writing 2 power of 24. Which opcodes? Here look at 2 power 24. Let's take, I am writing as P. So P I am representing as a 1 address instruction. 1 address instruction. Can I say now, all of you? 2 power 24 1 address instruction is possible or not totally? Yes or no, all of you? 2 power 24 required. But so I want to know accept even like let's take Q, I am taking Q nothing but as a 2 address instruction. 2 address instruction. I want to support among this Q, P plus Q, if I write it P plus Q, both supporting like among this only, right? If I want to support Q 2 address instruction from 1 address instruction, how many things you have to invalidate? So now I am taking weight 2 power 8 you have to invalidate, remove from that. Now this should also support what? R nothing but what? 3, R is nothing but now 3 address instruction, right? 3 address instruction. To support this one 2 power 16 to be invalidated. And this expression, if we use all the types of questions we can solve from this area. Suppose let's take other case, is a 0 address, 1 address, 2 address also you can say. Let's say example, they say 0 address are there, 1 address are there, 2 address are there. This many 0 address, this many 1 address, how many 2 address instruction possible? Now you treat this is a 0, this is 1, this is 2. Sir, only 0 and 1 is given, sir. 0 and 1, you can remove this only, this will format. Sir, given 0, 1, 2, 3, 4 also, like this you can add it, increase here. This is a one expression which solve all types of problem in this area. Just need to be substitute all of them, one of them either P, Q, R need to be find out. I hope you understand this question, this statement. This type of questions you can expect, right? So, we'll see, and other type of question will be memory sizes. So, let's take one question I will be taking here. They given one question, you see, look all of you. Consider a processor which has the following pin structure: AD0 to AD23, A24 to A39. AD0, AD3 is a time multiplexed pin with A address and data. Time multiplexed nothing but some pins are acting for address as well as data. D for address, A for D for data, A for address. Now so address how many? A0 to 23, 24 to 39. Total address has 40. Data has how much? A0 to 23 nothing but 24 is the data. So data is overlapped with time address pins only. Time multiplex means this can be acted as address and data only, but not at a time. Fine. Processor contains 256 registers. 250 registers also there. An instruction is designated with 4 fields are there. 4 fields are there. One is opcode, register address field, memory address field, 16-bit immediate data also there. Processor performs 150 operations, total instructions, sorry, opcode. If a program contains 100 instructions, then how much memory space is consumed by the program? The program containing 100 instructions are there. First we need to find out instruction size. We can multiply number of instructions, we will get the program size. Now options given, the total memory consumed 650 bytes, byte manner, word manner given. Let's first of all get the instruction. They said instruction has 4 fields are there. What are the 4 fields are? Opcode, and one is the register address field, other is memory address field, other is what? Immediate data. This is 16-bit given. And opcodes, how many are there? 150 are there. 150 to address, how many bits required? 8 bits required. Registers are how many? Registers 256, nothing but 8 bit required to address them or not? Yes or no, all of you? Yes or no, all of you? Do respond. Now memory need to find out what are the memory address bits. So they said clearly, no, AD0 to AD23, A24, 39, total 40 bit. Is it not 40 bit? So 40 bit address. Now this is 16 bit is there. Total how much? Total instruction size. So 16 plus 16, 32, 72 bits. 72 bits. This 72 bits nothing but how many? 9 bytes only, right? 9 bytes only. 9 bytes. Now space per program, if you see, how many instructions are there? They said 100 instructions. Each instruction is 9 byte. So 900 byte. In a byte address pool, 900 required. Suppose space for program in terms of words, I am taking words. Okay, 900 byte. So I have to divide by one word. What is one word? So one word size depends on data bus. What is the data bus? They said D, very D, 0 to 23. 0 to 23, 24 bits. 24 bits nothing but 3 byte. So one word is 3 byte. Byte cancel, 300 words. So if it is byte aligned memory, 900 bytes required. If it is word addressed memory or word aligned, 300 words required. Now we can go and see the options. So 900 bytes, this is correct. 300 words, this is correct. So option A, D correct. So this way you can answer the question now. Look at another question. Consider a processor with a 16-bit instruction. The processor has 12 registers and support 2 address instruction as well as 1 address instruction. Both are supported. If the processor support 5, 12, 1 address instructions, then how many 2 address instructions are formulated? See this type of questions. Now what is instruction size? Take instruction size. Instruction size is 16-bit. It is supporting 2 address as well as 1 address. Let's take 1 address. So now here is opcode, right? Here is operand field, address field. Which address field? Register address field. Because how you understand registers, sir? They mention 12 registers are there. So register address field only is address field only, right? 12 register nothing but how many bits required, sir? 4 bits required. 4 bits required. Now how many opcode bits possible? 16 minus 4 nothing but 12 bits required here. Now what is the address instruction? 1 address or 2 address? 1 address only. Suppose I want to make it a 2 address instruction. Now 2 address instruction 1 1. So this is register 1, register 2, 2 addresses. For this 4 bits required plus 4 bits required, right? Now opcode in this case possible how much? 4 4 8 over. So 8 only possible, right? To support the 2 address instruction, 2 power of 4 instructions are invalidated from this one or not. Now can I write same expression? 2 power of 12 will be P. P is nothing but 1 address. To support Q, Q nothing but 2 address. 2 power of 4 instruction to be invalidated. Now what they give, this process support 5 12 1 address. So can I substitute in this expression? 5 12 is P plus Q into 2 power of 4. Can I find a Q value or not? What is the Q value? What is the Q value? So now you can subtract, right, this. So this you can subtract now. 2 power of 12 minus 5 and 12, minus only, right? Divided by 16, this value is how much gives? 2 power 12 by 16 if I do, 2 power 12, 2 power 4 I can write. So 2 power 8, 2 power 8 minus this 2 power 9 by 2 power 4, 2 power 9 by 2 power of 4, right? 5 will get 32. So 256 minus 32, 224, is it not? So option B is right or not? See, so same expression or not? First thing given, first minimum thing you take up, then add rest remaining instruction format. So like couple of times they have framed in this area, so just go through also this area, also important. Fine. So next aspect we have to observe addressing modes. Here theoretical questions can be expected or numerical type question expected, match the following questions also we can expect. So you might have studied implied addressing mode, immediate addressing mode, right? Third one, direct addressing mode. Fourth one, indirect addressing mode, right? Fifth one, register addressing mode. Sixth one, register indirect addressing mode. Indirect addressing mode, is it not? Indirect. Seventh one, PC relative addressing mode, is it not? PC relative addressing mode. Eighth one, base register addressing mode. Ninth one, indexed addressing mode. 10th one, auto increment or decrement addressing mode. This is modified from the index only, auto increment or decrement. So these are the 10 addressing modes will be there. Theoretical, like sometimes they may give a instruction, they'll ask what kind of addressing mode being used, or sometimes left side list of instruction, right side addressing mode, you have to map it, or sometimes they may give some data, also they can ask some numerical type questions, or sometimes they give some instruction, they say this addressing mode already I am using, how many memory operations required to perform this instruction. This type of questions we can expect, properly revise it. How to identify the various addressing modes? Look this call, observe all of it. So suppose some examples I am taking. I am performing add of a register R1, #50 is given, okay, like this. So this is a register direct addressing mode, this is immediate. Whenever you understand constant is there, constant with hash symbol is there, I symbol, hash symbol or I indicate immediate addressing mode, right? Now suppose register R1, register R2 like this given, this is a register addressing mode. To understand, example 1. Example 2, add a register R1, register R2, let's take 500 is given. Whenever direct constant is there, is a memory address. So direct addressing mode, this to a register addressing mode. Now simply you understand some constant or square bracket, some like this is given, indicate a direct addressing mode. Example 3, I am performing add register R1, register R2, 500 given. Whenever such parentheses are there, it is a memory indirect addressing mode. Okay, required 2 memory operations. Why? To fetch this operand, one is for 500, other is for this one. 2 memory access will, this nomenclature if you write it, m of 500 like this, m of 500 or like this, you understand, plus R2, this results I am storing in R1 like this. 2 memory access required, 2 memory access required. Example 4, suppose add register R1, register R2, 500 given like this, understand. So this is the memory indirect addressing mode, indirect addressing mode, clear line. This is register parenthesis there, register indirect addressing mode, register indirect addressing mode, register indirect addressing mode. Suppose if I ask question, during execution cycle, not fetch cycle, execution cycle, how many memory operations required, how many memory access required. So now during execution time I have to fetch this operand, then I have to perform addition, storing into R1, right. This is required 2 memory because this is what, indirect addressing mode. So this is one register access, one memory access, one required. The storing will be in register only. So total 3 memory access required. 3 memory access required to perform this operation. Now understand, parenthesis or at the rate symbol is given, this indication indirect addressing mode, indirect addressing mode, clear. Example 5, suppose add register R1 at the ref R2 at the rate 500 given. This again see, understand, this is a indirect, memory indirect, right, memory indirect, memory, this is what, register indirect, register indirect, this is the observation, clear, clear all of you. I hope you are able to understand. Everyone, those who are watching, try to respond, try to respond. Are you able to understand differentiating these things, various addressing mode, how to address it, how to identify it, and like if they ask question, how many memory access required, so you are able to answer it or not. So you can copy, respond now, those who are watching. Next one, another example we will see, 4th and 5th. 6th example, add register R1 20 of register R2. Are you getting my point? Then I am writing like this, you understand, at the rate of register R3 is given. What are the addressing modes are there here? This is simply register, okay, register indirect addressing mode, indirect addressing mode. What about this, some value is added, right? They did not specify whether index register or this one, either it can be base register or it can be index register, index register. Why? In both the case some offset value we are adding, is it not? Either base register, index register we take, offset value we added to part of the register. In base register, some offset value we added to base register. In index register, offset value base, like in index register, understand, array base address we added to index value. So either can be index or base register based on the options which you can select it. I hope it clear. And there may be question they can make it on PC related addressing mode, right? PC related addressing mode purpose is what? Branch type of instruction. Like whenever branch is taking target address need to be calculated based on the current PC value. Some offset we need to add it to get the what target one. So this type of questions also we can expect now. So these are the major observations from this addressing modes. Okay. So I hope it is clear. Now incrementation decrement is based on this only. Register increment like decrement increment will happen. Now when it comes to this, from this chapter instruction pipelining is much important. Every year we can expect a question from this one because happening from the all previous year gate questions if you see. So one question definitely is there in each year of the gate from the instruction pipeline. So, instruction pipelining, okay, major thing first initially speed of factor. The first thing you need to know, speed of factor, okay. So, before this speed of factor you understand cycle time, very important, I am taking TP. Cycle time of pipeline will be maximum of stage delay plus buffer overhead or latch overhead or register overhead. Second important, cycle time of non-pipeline, cycle time clock, cycle clock time here. Non-pipeline will be simply you have to take maximum like sum of, okay, sum of all stages delay, sum of all stages delay, or simply count the number of clocks also, count the clock numbers. Now, third one, speed of factor will be time with non-pipeline, right, time with non-pipeline by time with pipeline, okay. So, this non-pipeline time nothing but number of instructions multiplied by now number of clock cycle required for each instruction, clock cycle time means what, TNP divided by, so now k plus n minus 1 into this cycle time of TP. This is important thing to be noticed. This is important thing to be noticed, okay. Further if simplification if you see, S equal to whenever the cycle time of NP and TP is same, then n into k into TNP divided by k plus n minus 1 into this TNP, I can write it, both cancel, nk by k plus n minus 1. Understand one thing important here. When n is large approaching to infinity, k going to be constant, is it not? Constant in the pipeline down part. The speed of factor now nk by, what if n is large, k is a constant. When n is a large, k is constant. I can ignore k, that means n. So, yes, ideal pipeline can have speed of factor how much, k. This is a major important thing to be observed, When number of instructions given, we can achieve what, when number of instructions increased, maximum achievable, like not as maximum ideal pipeline can possible equal to number of stages. This important thing be noticed now. Third point. The fourth point you understand here, one thing, clock per instruction average in the pipeline will be 1 clock. This is blindly you have to make it. Average we can prove it because when keep on increase number of instructions, first instruction will take full pipeline, after that every clock we will get output. That is the reason average clock per instruction will be 1 in the pipeline. Fifth point, clock per instruction average non-pipeline will be what, k clocks. What is why k? K stages, each stage require 1 clock, k clocks will be, this you understand. Sixth point, clock per instruction, sorry, so one more point, sixth one will take, we got speed of factor, right? So, we will take efficiency of the pipeline. Efficiency indicate, utilization of the pipeline. How much I utilized? Ideal how much possible? Ideal is k, is it not? Ideal is ideal pipeline. Ideal per maximum speed of factor how much? Equal to k state k. Out of it's how much as you observed, how much utilized? Yes, S is achievable, achieved speed of factor by achievable. This is efficiency. S by k, then k stages speed of factor, all you can calculate it. Like this is important thing to be observed now. Important thing to be observed. Is it clear all of you? Is it clear? Chalo, now, so sixth, seventh important point, understand. I said clock per instruction average will be 1, right? 1 I said, 1. If no dependency is there, no dependency among the instructions, But what happens here, clock per instruction average can increase more than 1. I am taking as a delta. Why? When there is a dependency. So 1 plus some delta clocks can happen. Delta just I am writing delta symbol. Delta clocks required if there is a dependency among the instructions. Dependency among the instructions. Fine. What is delta? Delta indicate what is the percentage of dependency, like frequency of dependency multiplied by number of stalls increase, number of stalls, stall cycles. What is frequency? Do not confuse. Suppose 20% dependency instructions are there, 30% dependency instructions are there, 50% dependent instructions are there. Each dependent instruction causing 2 stall cycle, 10 stall cycle like this, you have to take it. Then when I multiply this one, what happens? The clock per instruction will increase. Clock per instruction will increase. This is the important trigonometries. When you have to apply this one, when there is a dependency, because generally data dependencies, like no dependencies in the instruction pipeline, see data dependency, control dependency, structural dependency, all the things will be there, right? Yes or no? You are getting my point. So these are the performances. Basic thing to be noticed here. Right? Now see what type of question they'll ask here. From performance related of instruction pipeline, they'll ask find the speed of factor, find the efficiency, find the number of stages by given data, or they can compare 2 pipelines, which is better, time consumption, or sometimes tabular form they'll give it. There are set of instruction, each is a different clocks required, total how many clocks required, pipeline. These types of question comes. This is the first aspect. Second aspect of the instruction pipeline is hazards. Hazards are dependencies. Hazards are data dependencies. These hazards are basically classified data hazard, and next one control hazard. Third one is a structural hazard. Structural hazard or dependency. Okay. Generally, this arithmetic logical operations causes the data dependency problems. And branch type of instructions causes the control dependency, and resource limitation causes what? Limitation causes the structural dependency. And you might have studied from the solutions also. For data dependency, operand forwarding is a major one, or compiler based solutions also you can use it. When it comes to control dependency problem can be resolved having separate pipelines, multiple pipelines I can place, or detection of early detection, nothing but data decode stage can be modified to detect the branch. If it is the branch, then try to generate address there only. So we can reduce the branch penalty to 1. Other is branch delay slot. After branch, every branch instruction, keep that empty slot, place it what? So unit operator forwarding, definitely I can explain. No problem. Stay for some time, I'll explain. So I was talking about control dependency, right? Either use multiple pipelines or use the early detection or branch delay slot, or prediction methods will be there. Branch prediction method. Either one of the method can be used for dealing with control dependency. Structural dependency nothing but duplication of the resources, means instead of one ALU, 2 ALUs you use it. Instead of single bus system, I should have multiple bus systems. Then only able to implement this instruction pipeline concept properly. Otherwise, we cannot do it. So as per the Soumil request, will work out on operand forwarding. Let's understand. So I'll solve later this question. Look at, to solve the data dependency problems, to solve the data dependency problem, we use hardware mechanism called operand forwarding. Operand forwarding mechanism, we are going to use it. Right. What is operand forwarding says here? Try to forward the operand dependent instructions before storing it. Before storing, you forward it. That's a simple mechanism. But for this to implement, we need hardware support here. First of all, let's understand how instruction will create a data dependency, right? Now see, data dependency nothing but suppose I am taking addition of R1, let's take R2 and R3. 3 address instruction I am taking. Another instruction subtraction is there. Let's take, you understand here. I am storing it, let's take R5, R1 and R4 is required. Look, understand. If I execute these two instructions and let's take 4-stage instruction pipeline. 4-stage instruction pipeline. Let's take stages are fetch, decode, execute and store are there. First understand, then I'll explain, no problem. Suppose if I write it in instruction 1, if I schedule it in instruction 1 on this pipeline, first I'll fetch. What is the name of the instruction? Addition, right? Fetch. Then I'll decode. Decode time only I'll fetch the operand. What source operand? R1 comma R2. R2 comma R3. R2 comma R3. Execution required R2 plus R3. Storing in where? R1 only. Let's take each stage taking 1 clock cycle time, 1 and 4. When this instruction decoding fetch is free, so instruction I2 I can fetch it what? Name of the instruction subtraction. Now when it is executing, we can decode. Decode means identify instruction as well as fetch the operands. What operand needed? R1, R4. But R1 is not available, right? Yes or no? R1, do you have availability now? R1 is available end of the 4th clock only. But I need. So hence force, second instruction used to like forcefully wait till this point only. So now here I can decode, then execute and store now. What happens? Number of cycles will increase or not? Soumil, tell me, number of clock cycle will increase or not? So decode I cannot do because operand R1 is available, it will available end of the R4, end of the 4th clock. Then the decode can be done. And second instruction need to be wait. So now number of clock cycles increased, it will affect on speed of factor. How this problem can be solved? By using operand forward mechanism, if you observe it. So let me take this one. What operand forwarding saying that? Suppose instruction 1, when I fetch it like this, understand? Fetch, add, okay. Then clock number 2, decode R2 comma R3 decoded. Then store, execute, right? R2 plus R3. Then storing happen R1, clock number 1, 2, 3, 4, right? Instruction I2, so fetch, what subtraction, name of the instruction, decode. So now decode, what you can do, available register you decode it, do not wait for unavailable. So we need to decode which one, R1 or R4, but R1 is not available, but R4 is available, so you can decode R4 here now. Or else what you can do, R2 also decode, take it R2 read the dummy value, because you have to update the R1 value. I am saying the available R4 you can take it. I need R1 available end of this one, right? So right now you can read dummy or you can not read also, no problem. Now during execution time, what happens here? What execution required? So now see this results, this when you are executing, once execution over, results available end of this register or not? Every stage is what? Preceded and followed by registers. We call latch or buffer register, something, correct? When execution or results will be available or not here? Is available here, then after that we store in the memory, store in the register here. Operand forwarding nothing but after this execution, before storing only forward this location, So now what you have to do? Subtraction what? Subtraction of what? R1 minus R4. R1 I got, R1 nothing but we got R2 plus R3 content only we got, minus R4 I can do it in this one. In a store R5, register R5 I am storing at 5th clock, you see. Problem is resolved or not? Soumil. So what I am saying that end of the execution stage, register is there, we store it. we kept here buffer, then we are storing it back to register here. You forward and store it R1, that's meaning. Just forward the result and store it R1. That's the meaning of forwarding. And practical, how this is possible? See, this execution stage nothing but same stage only, na? This stage is same only, or do a double stages? Same stage only, I am doing different work, different instruction work, right? When I am storing the register, when I start new instruction take up, then feeding forward only. So now I will show you the diagrammatical I can show you. We have a fetch unit, right? We have fetch unit. Here is a register is there. Here is what? Decode unit is there. Decode unit is there. Then interstage buffer is there. Here is what? Execution stage is there. Here is interstage buffer is there. Then we have a store, right? Store. Instruction I1 I am taking, right? When you fetch addition and decoded something. Now when you are decoding, I can use this fetch of instruction I to fetch, right? Fetch I am doing. When executing, I am decoding here, decode I am doing. Now is the register, right? Register only, is the register only, right? Now you see, now understand, this execution stage only, right? Is the execution stage for second instruction. Here is a register and here is a store will be there, store will be there. Now see, I1 results is R2 plus R3, results available here only, end of the register only, right? Simply I am forwarding to here only, that's it. Simply forwarding to this location only and given to same stage only here, you see. This is the meaning of operand forwarding. Sir, so suppose the previous execute stage takes 3 clock cycle, then can you explain with an example? So now what is this taking 3? Whatever number you take, 3, end of the 3 only, na? Example I have taken 1 clock cycle. It is taking 3 clock cycle, right? Can I use, suppose, do you understand, if you take it 3 clock cycle, can I use this execution stage before 3 clock? Is it possible to use? Somebody already using the stage, can I use for other instruction? Sawmill 2, you need to respond. You need to respond now. I am taking this instruction taking 3 clock cycle. At the second or first clock or third clock, can I use that hardware to a second instruction? Tell me, can we be able to use it? Right. So now you understand, this is a stage taking 1, 1, 1. Suppose 1 clock, 2 clock. End of the stage only you forward it. End of the stage only we have register, right? Here buffer, right? End of the stage only you place in the buffer and that is going to be storing back to register. So before storing you forward into same stage only, na? Because this stage only I am using here, right? You see the diagram, see. Is it different stages? Are they different or same? This execution, are they same or different? Think and tell me, Sawmill. This stage, are the same or different? No response needed, tell me. The stage execution stage, are the same or different or duplicate, 2 copies are there? No, that is a mistake. Such a cases, suppose if I say, if both are different stages, nothing but, if 100 instructions are deployed, I do not have 100 execution stages, 100 fetch stages, 100 decode stages, 100 storage. So that's not going to be concept of pipeline. That's not going to be pipeline concept. We have only 4 hardware, fetch, decode, execute, store, nothing. We do not have duplicate here. You are getting my point? The secondary thing, how we are going to solve the structural dependency, the second thing. Right now, you understand, if I am doing execution, nothing but, I will complete this execution, then same stage I will use for other instruction only. Stage is same. It is kind of, I will produce output, I will feed it to here again. So produce output, feed it to again here only. Is it not? See. So now I produce output here, same output I am giving to whom? Same stage only. But this output given to same stage for second instruction. Now we have to forward. How to know, sir, I have to forward? Very simple. Compiler help is needed to implement this concept. Compiler, at least you have to identify there is a dependency. Every consecutive instruction you check, if there is a dependency, you give some information. So that information I will put it to like a 2 by 1 multiplexer. If dependency is 1, so when there is a dependency I will forward. No dependency, simply I will decode it. So simply we are waiting for the previous execute to finish and then we are using it for the second. That's it. That is only forwarding mechanism. When I draw the diagram, it looks like a copies will be there, but actually it is not there. It is kind of like this, you understand. But I cannot say like this feeding. It is happened next clock, right? I cannot feeding, I cannot say because it is a clock number 1, clock number 2, 3. This is 4. Clock number 4 is happening, right? That is the reason I shown like this here. Saumil, able to understand? Question is comes like how to know that I should forward or simply suppose there is no dependency, I should not require to forward the result, right? So compiler help is needed. Compiler we should say that you should how to identify dependency. You might have studied read after write problem, write after read, write after write. So that with these cases we can compiler can identify there is a dependency, that information passed to control unit. So now I can apply 2 by 1 multiplexer. One is connected to this end of the execution, one is connected to decode. If control unit is 1, you forward, otherwise you simply decode it. That is additional hardware support is required to implement this mechanism, but most of the data dependence problems are resolved with what? Operand forwarding. There are software approaches also we have compiler based, but it's costly nothing but lot of overhead. Compiler overhead is very high. So we depends on hardware only. Hardware is mechanism faster. Fine. So what else you want to discuss with me from? So let me know what are the things you have. Like if you have any doubts from instruction pipeline, let that topic can be discussed. Or this is clear? Respond. Now let's see one question from this is branch type of instruction. Nothing but you understand. Control dependency, control hazard. Let's try to solve the question here. Consider a pipeline which is operated with 1.6 gigahertz frequency containing 8 stages. Pipeline allows overlapping all the instructions except the branch instruction. When branch instruction occurs, it won't overlap, means penalty will be there. The processor stops fetching a sequential instruction after the branch instruction until the outcome is known. This is very important line. What is whenever the branch instruction is encountered, next to sequential instruction not going to be fetched until outcome is what? Either branch will take or not. Until outcome comes, it won't fetch. The penalty will be there when branch will encounter. This is another important. All the instructions output is available end of the execution at last stage only. 8th stage is there, na? 8th stage will the address generator. Our results also comes are at 8th stage only. And branch instruction target also available at 8th stage only is telling. Next. Program contain 40% branch instructions. Among them 60% are conditional branch, in which 40% does not satisfy the condition. When condition is false, then the following instruction is overlapped. Then what is the efficiency? Up to 2 decimal places they are asking. Efficiency they are asking. How to calculate the efficiency? Very simple formula just now I given. Efficiency. What is efficiency? Achieved speed of factor by achievable speed of factor. Efficiency general term, it can be asked from CO point of view, OS point of view, computer networks point of view. Computer network point of view, suppose if you take it 2 nodes are connected, and what is the efficiency of the sender? That depends on, you understand, transmission time by total time. Is it not? Transmission delay by round trip time. Is it not? Here is speed of factor by number of stages. Yes, number of stages. Why? What is the efficiency? Utilization only. How much percentage of utilized? Total capacity of the pipeline is what? K. Maximum achievable speed of factor. How much? Number of stages. That is ideal case. In practice, not possible because there are a lot of overhead in the pipeline. You cannot achieve practically K, but mathematically we proven. See, we proven. See, when cycle time of non-pipeline and pipeline same, Nk by K plus 1, when N is large, K is constant, then ideally what K will get. This mathematically proven, but practice is not possible. In practical, it is not. Why? Because some overhead will be there. But with this respect only I can write achieved speed of factor by achievable S by K. So, S by K we need to find out in this question. S by K we need to find out. S by K. S by K. So, S by K means what? 8 only here. S is what? Speed of factor. How to find out the speed of factor? Tell me now. The speed of factor with what? Time with. Are they given number of instructions? Not given. Let us take one instruction time. So, average in instruction time non-pipeline by. So, average instruction pipeline, right. This is K clocks. Is it not K clocks? Divided by 1 clock only. Is it not 1 clock? All of you, both of you, Saumil and Mridula, do you agree this one? K clocks only required in non-pipeline. One instruction non-pipeline will take how many? Number of stages. Each stage take 1 clock cycle. Means what? K clocks means K number of stages are the K clocks required. In a pipeline average 1 clock only will take 1 clock. K by 1 I can write. But important factor is here. When there is a dependency, the down point, when there is a dependency, more than 1 required, 1 plus delta clocks required. Do you remember I given one point also, a note point also given as a note point. You see, average clock per instruction, 1 if no dependency is there. If there is a dependency, some extra clocks required. What is the delta? What is the rate of dependency multiply by and stalls for each dependent instruction. Stalls for each dependent instruction. Stall frequency by stall number of stalls. Indication 20% dependence, 30% dependence. Each dependent instruction, how much time is taking extra clocks, that you have to multiply. That is what delta. So, this is overall thing. This is overall thing. This overall thing. So, now K already know 8. So, here is 1 plus delta value we need to find out. So, now I am writing that's part only. Clock per instruction average in the pipeline will be 1, but because of dependency delta extra required. Now see 1 plus delta. What is delta? They said here 40%. They said program containing 40% branch instructions. Tell me ma'am, when they say 40% branch instruction, nothing but 60% are non-branch, is it not? Hello, respond. 40% branch instruction nothing but 60% non-branch nothing but which will not cause any penalty. They may take year 1. This 1 indicate what? Here 1 indicate what? 60% are non-branch. I am a mathematics, you properly observe this one. Now, out of 40%, they said 40% branch. Among them, 60% are conditional branch. 60% are conditional. If 60% are conditional, can I say 40% are unconditional? Yes or no? Can I write like this? Respond everybody. Those who are watching respond ma'am. 60% are conditional branch, 40% are unconditional. Can you give example for unconditional branch instruction? Can you give example for unconditional branch instructions? Go to. Is it not simple? Go to, right? Now tell me, go to instruction will cause the penalty or not? It is a branch only, right? Also they said clearly in the question. All the stop fetching the sequential instruction of the branch instruction until the outcome is known. Now 40% unconditional instructions will directly jump or not. If they jump, there is a penalty or not. Now tell me, all of you, So let me write penalty later. Now you tell me. Come into conditional branch. Conditional. They said one more point also there. 60% are conditional branch in which part 40% instruction does not satisfy the condition. So now can I say 60% are satisfy the condition or not? 60% are satisfy the condition plus 40% are not satisfying nothing but, so no, penalty will be 0. Now my question is 60% conditional branch instruction, so condition is satisfied nothing but they'll jump for a target instruction, yes or no? If they jump for a target instruction, there is a penalty or not? There is a stalls or not? All of you respond. Those who are watching, you should respond now. 60% of conditional branch instruction branching as taken, they said satisfied. If there is a penalty, how much penalty will, how many extra clocks will happen? Somebody tell me. How many extra clocks will happen here? How many extra clocks will happen? They said clearly, results are available end of the register, end of the stage, last stage. Last stage is the results producer or target address generator, right? Now 8th stage nothing but 8 minus 1, 7 clocks will be the penalty. Do you agree all of you? This 7 is correct? Very good. Stage minus 1. Saumil, do not, please understand, not number of stages minus 1. Always we should understand which stage is generator address. Sometimes gate people they'll confuse. 5th stage of the 8th stage instruction pipeline produce the target address. 5th stage of the 8th stage instruction pipeline resolve the target addresses. In that case, tell me what is the stalls, extra stalls will happen now. Penalty how much? In that example. 5th stage of the 8th stage instruction pipeline generating the target address. In that case, what is the penalty? 5 minus 1, 4. I hope this is clear. But since in this question they mentioned last stage, that's the reason we should be 7. Now tell me 40% of unconditional also will create a problem or not? Unconditional jump directly, they won't, even you are not, at least you have a chance. If condition is not satisfied, sequence instruction will be overlapped. They said clearly, no? When the condition is false, the following instructions are overlapped. So no penalty. This is no penalty. But jump, unconditional jump will create a problem. 7. Now you simplify mathematics. 1 plus, so 0.4, 0.6. So 0.6 into 7 plus 0.4 into 7. Tell me this value, all of it. Tell me this value, how much it will be. CPI average in the pipeline. Tell me this value. Fast, calculate fastly. Tell me the answer. Do respond, ma. Do respond. What is the answer you got? Saumil, one point. I think you should get 3.128, I guess. This might be giving 2.128. 2.1 plus 2.128, 3.8, very good, very good, very good, very good. Now, speed up factor. The speed up factor S equal to 8 clocks divided by 3.128 clocks, right? this value is almost 2.55 we got. Now efficiency will be so achieved 2.55 divided by out of 8. What is the value in terms of percentage? Are you getting 31%? Calculate. Approximately 31%. Tell me fastly. Yes. Now second question, if I ask you, clock per instruction, right? Clock per instruction average in the pipeline, how much you got? 3.128 clocks will got, right? If I ask you in terms of time, can you tell me in terms of time? So 3.128 into cycle time of P, you have to find out cycle time of P. Now 3.128. So now what is the clock rate given in the question? Clock rate, how much given? Clock rate 1.6 gigahertz. Can you tell me in terms of time? Can you tell me, all of you? In terms of time, tell me for instruction, one instruction, what is the time for one instruction in the pipeline? What should I do? This divide by 1.6 gigahertz or not? So what is the value? 3.128 divided by 1.6 nanosecond. This gives how much? Fastly. Not 1 by 3.16 because it is not 1 now. First of all, clock per instruction in the pipeline not 1, 3.128, right? 3.128 only. So 3.128 by 1.6 only I should do it. Giga means I have to express in terms of nanoseconds only. How much this giving? Mridula, that is correct. 0.625 nanoseconds is correct. Okay, 1.95 nanoseconds we got. Now in this moment, if I ask you question, all of you, what is the throughput? It is this type of questions also they'll ask. What is the throughput of the pipeline? Tell me now. How to get the throughput of the pipeline? Throughput means what? What is the throughput here? Definition of throughput. Again, throughput is general term. Respect to COA, respect to OS, respect to computer networks, you get the question. What is the throughput? Throughput always defines how many words transfer per second or how many instructions are executed per second per unit of time. How many programs executed per unit of time in case of operating system point of view, correct or not? Now simply, so one instruction takes, how much here one instruction taking? One instruction take 1.95 nanoseconds. I will allow you to execute 1 second. How many instructions you can able to run it? Is it not throughput? So now throughput is nothing but, so this is a question mark, right? Is it not? So 1 by 1.95 nanoseconds. 1 by 1.95 into 10 power of minus 9 seconds can I write? This also can write 1000 by 1.95 million instruction per second. Can you tell me what is the value? All of you. All of you can tell me what is the value of this? Thousand by 1.95. Throughput is asking question possible. 5128, 5 to 1.8, 5 to 1.8. So can I round up like? Sorry, 5112, right? 513 million instruction per second. Can I round up? Yes or no? All of you. Can we round up like this? Yes. So you should be careful, such questions they'll frame it. And branch related things ma, lot of questions can be framed. Simply they'll ask what is the clock per instruction also. So much data give it, they'll ask here efficiency they ask na, they can ask what is the clock per instruction, simply this is answer, or speed of factor, or efficiency, or throughput, or like they can also say 1000 instructions are there, program 1000 instructions, how much time required to compute. So simply such cases, one instruction this much takes, 1000 you multiply, you will get answer. Asking program time, asking speed of factor, efficiency, throughput, and giving two pipelines also. Sometimes they say, so they giving this data same, there are two pipelines running, one pipeline this many instruction, other pipeline this many instruction, they can ask the comparison also. So we should be very broadly, you have to look into these are the areas from especially branch type of instruction, control dependency ma. So aram se you can solve the questions. Chalo, now quickly we will see what things can be addressed from IO organization, majorly DMA, that's a DMA only. Now data transfer methods if you observe, one is programmed IO we have, right, yes or no? Programmed IO will be there, and second one is what, interrupt driven IO will be there, interrupt driven IO, third one is the DMA, okay. These are the data transfer mode and DMA, main thing. From DMA, okay, two types of questions we expect majorly, 2 or 3 types of questions, DMA. So I hope you know the DMA principles, how it is works. Simply to effectively utilize the virtual memory concept, understand, virtual memory concept under like demand paging environment. Hardware support highly needed, that's a DMA control should be there. Meaning you understand, whenever operating system point of page fault is occur, the page we need to bring from secondary memory to main memory, right? Runtime only, right? Page fault occur, runtime only, right? Virtual memory concept says that entire program not required to keep into main memory, some part you can keep, remaining keep it secondary memory, runtime only you can fetch it, right? Runtime fetching should be very fast to increase this, IO operations, to reduce IO operation time. The separate module we kept in a computer system, that is nothing but DMA. DMA used to transfer bulk amount of data from disk to memory, memory to disk here. Whenever such environment is happening, when page fault occur, page needs to be bring from secondary memory. Now virtual memory manager informed to device manager informed to device drivers, drivers are informing to device controllers, device control put a request to DMA, read a concern page. Now DMA put a request operating like CPU, I need a system bus to be transferred. When CPU gives the system bus, it is also takes the data from CPU saying that how much data need to be transferred, from where to transfer, either reading or writing. So DMA installation should be done by the CPU. Once installation over, so automatically page will read from secondary memory to main memory. And DMA will work under 3 methods, right? One is cycle stealing mode, one is block transfer mode, third one burst mode. Burst mode nothing but, so DMA will not release the system bus until entire data transmission is over. Under cycle stealing mode, DMA will use the system bus for one word transfer, release the system bus. Under block mode, one block will transfer and I inquire for the system bus. Now they can ask question, first question, percentage of the time CPU is blocked under cycle stealing mode given by what? CPU is blocked under cycle stealing mode given by expression we have Tx by Tx plus Ty into 100%. This you have to observe. I repeat, first type of question, they give so much data, device rate this much I want to transfer time this much will be there. Now what is the percentage of the time CPU sitting ideal or block state under cycle stealing mode? Under cycle stealing mode what happens, I said, one word you transfer, release the system bus given to the CPU Again you inquire after the instruction cycle. Now here is DMA waiting time is more. CPU will be only blocked during transfer time only, is it not? During transfer time only bus being used by the DMA, right? After transmission, now bus will released only. Now see, that's what Tx is the transfer time. By transfer time plus Ty is what? Preparation, word preparation. It is depends on the device rate only. Suppose device is running 100 kbps per second. I want to read 2 bytes of data. You ask like, you are 1 second this much you transfer, 2 transfer to prepare 2 byte, how much data time required? That is what Ty. You write it, Ty indicate reading capacity. How much time required to read a bytes of data from disk? What is the Tx? Transfer time. So transfer time by transfer time plus this one you should understand. Second is what? Percentage of the time CPU is active or contributing under burst mode, They won't specify direct burst mode, they say how much percentage of the CPU contributing or active, given by same I am using Tx by Tx plus Ty into 100%. Now here Tx is not transfer time. Under burst mode what happens, burst mode? Once you get the system bus from the processor, DMA will not release the system bus until entire data transmission over. A file has 64 KB, a file size has 64 KB. Once I get the system bus, until transmission of 64 KB, DMA will not release the system bus. Now tell me, in this mode, either DMA or CPU, who is waiting more time, and which one has a more waiting time? Can you tell me all of you? Under burst mode, so which either DMA or CPU is waiting time more? Which one is having more waiting time? Yes, Mridula, Saumil, respond. If I use burst mode, so among these two, either CPU or DMA, which is having more waiting time? Which is having more waiting time? Respond. Try to respond, try to respond. Under burst mode means what I said you, DMA will take a system bus, it will not release until completion. Yes, obvious CPU waiting time is more. They won't ask how much waiting time is, most of the time waiting only, most of the time blocked only. That's not active, they ask, no, CPU is active, nothing but what happens? Before releasing the system bus, CPU initialize the DMA. What is initialization process? You know, right? How much data you should read it or write it, from where you read it, address, data count register, address count register, and read or write signal given by the CPU. This process is known as DMA initialization. During DMA initialization, CPU is active, otherwise it is blocked only. So now Tx represent now here initialization time by initialization time, Ty transfer time. Transfer time nothing but I should know. So device rate is 10 kbps per second, 1 second 10 kb if you transfer. I want to transfer or read one file of 64 kb. How much time required? Same like a Ty you calculate here. Only changes Tx. Tx is not transfer time. Here is what? Preparation time. In a gate paper they will give this many clock cycle, this much time required to initialize the DMA, and this much file I want to transfer. In this scenario, what is the percentage of the time CPU is active? CPU is active. This expression you can use it and get it. And other thing also, number of time, how many times system bus required to transfer this many files. So these are the types of questions I saw from previous year papers, and sometimes they do comparison also. They do comparison between, no, suppose I am using programmed IO, it is taking this much time. If I replace by this one, so how much time it is increased, what is the speed of factor? They do these two comparison also. GATE 2023 paper, go and practice, they did the comparison between these two, programmed IO and interrupt driven IO. 2005 paper, there is a 4 marks or 2 marks question framed. They did the comparison between these two. Another year they did the comparison between these two, like this. They give a time or they give some program, they say some information, based on information you can able to calculate. So these are the major thing to be focused from the computer architecture. I hope this session is useful to you, and those who are not able to attend the live sessions, try to watch this complete session, because from beginning data representation, from fixed point, floating point, memory hierarchy, main memory, cache memory, address mapping scheme, their comparison, and we have discussed like cache address updation methods, write to write protocol, their formulas also written, instruction format, their encoding and various addressing modes and identification and instruction pipelines, and this DMA. These are the major things I have discussed in this session. Last moment revision, like you see, the prior to the gate exam example, 2 days before the example, 2 days before the example, 3 days before the example, every subject quickly you want to revise it. This 2 or 3 hours is going to be help you a lot. See, 3 hours one subject you are revising, right? 3 hours another subject. So even I have taken on 26th January, like same session on operating system also, you can watch that one also. Tell me, Somil, what is the question from memory? Tell me. Tell me the question from memory. Mridula, do you have any queries? Somil, tell me your query. And there are one more important thing, like what are the subject you would take up? At least last 10 years gate papers, try to practice it, because gate questions are giving the lot of, you understand, conceptually you can make it more clarity. Okay, so you should practice enough gate questions and other test series, so that you are able to answer the question. If a system uses a cache, TLB and page, so when the CPU generates the logical address, where is the data checked first? So if a system uses a cache, TLB and paging concept, so when the CPU generates the logical address, so where see my point you understand. So CPU generate the address, right? Address. This address we called even effective address also we can call, or logical address also called, or virtual address also we call. This address based on the combination of addressing modes, because we use now addressing modes, base address, offset value, PC value, all, you understand, right? Combination address will generate, right? Now somewhere here is a physical address, like somewhere memory will, here is a memory will be there. Maybe here also cache memory will be there, right? Maybe cache memory will be there. You understand clearly? First of all, we translate this one, okay? Translate, okay, logical to physical address. Two things can happen. First, no, I can give TLB, okay, TLB. Logical address, virtual, so because if TLB is there, first is going to be TLB. In a TLB, 2 entries will be there, right? Yes or no? TLB 2 entries will be there. One is page number and frame number will be there, correct or not? Anyway, this address we split it into page number and offset. We split it or not? We split it page number and offset. We take a page number first, because TLB, if it is there, I have to search first TLB only. I am searching TLB. For this page number, if you have a frame number, F plus this D, I will add it, I will get a physical address, right? I will get a physical address or not? Physical address. If cache memory is there, first I will go on cache memory. If miss occur, I will go to main memory. Miss case, I will go to main memory. This one way. Other way, when I am searching page number here, if it is miss occur, same page number I will search into page table. Same page number I will search in page table. So this give a physical address. Once you get a physical address, I will search into cache memory. If miss occur, then I will go to main memory. Now, which is accessed first? TLB access first. Clear? Samil? Samil Kumar? Sorry, Konar. Is it clear? Some gate question asked also, like no, effective address calculation happen before TLB access or after TLB, before page table, like this one question asked actually. One of the gate paper asked this effective address and logical or virtual address calculation will happen after TLB address generation or before TLB address generation. There was a question. It is before only. That's only my point. If TLB it, you will get a corresponding frame number. I'll pad with this D. I'll get a physical address. I'll combine physical address. I'll go to cache memory. If TLB miss occur, very simple, right? From operating system my point of view studied. When TLB miss occur, same page number I'll search into page table. So memory access required. I'll access the page table. If page table also miss occur, then what to do? It's kind of virtual memory, you said. I have to go to secondary memory, take the page, load into main memory, update the page table, even update the TLB, restart the instruction. When you restart, you will get address, split out page number offset, take the page number, now search in TLB, it is hit. If it is hit, take the address, go to cache memory, search. If miss occur, go to main memory, search it, given to the processor. This is only point. That's what memory is a crucial topic from this subject, OS and COA. If you clearly understand memory now, these two subjects can be mixed. Mixing is there here. That's what we can expect the question from this, a mix of these two. Sometime one of the questions they framed, they given virtual address, physical address, page size given, TLB having this many entries, 4-way set associative. They ask now what is the TLB value. They did not given blocks, they given page numbers, like page size is given. So do not confuse, same thing only, right? TLB is a cache memory only. TLB is cache or associative memory can have. Sir, how will be the memory updated in the TLB and a cache? How will be the very simple, very simple. Okay. Every process having its own page table, right? Every process having own page table. TLB common for every process. Whenever a page you loaded in a main memory, when a page is loaded in a main memory, first thing you have to update, page table is a data structure, right? You have to update. Page table is a data structure, right? You have to update. Or if there is a mechanism to immediately to update, TLB update. Otherwise, when you restart the instruction, so I'll go to miss occur, right? TLB miss occur, right? I'll go to page table, I'll access it. So when page you're reading now, we use address mapping schemes, right? So when you map to cache memory, then I can update. Otherwise, it's very simple, I can understand. First time when you load the page, you update page table as well as TL, both you have to update. Entry you update it. That entry may be replaced later, it can be replaced later, but you have to update. Either beginning of the program or when middle and page fault occur, that moment only we can update page table and TLB. I hope this is clear. Saumil. Yes, ma. Any other queries? Ask ma. So if the queries are not there, so you can join this Telegram group also. If further queries are there, can be even discussed. So will be replaced in the cache first, then after it goes to CPU, and then it is updated in TLB. Obviously, see when one page, what I'm trying to say, the scenario will happen. Whenever a page you loaded in main memory, right, then I updated page table as well TLB. This one thing. Now when you start accessing data, what happens? First, I'll take a logical address, I'll search in TLB. TLB will it. Okay, I got a physical address. I am going to access the cache memory. Cache is empty, not placed, right? Initially we won't place it. Empty, cache miss occur. So I'll go to main memory. Concerned block, I'll place it here and given to the processor. Now next reference. Again virtual address generate. I will search in TLB. Listen. Suppose if I get a frame number, I'll get a physical address. I will search cache, is now available because block I is moved, given to the processor. Case number 3. So third reference, virtual address generated, spreaded P and D, I am searching TLB miss occur. Then I will go to page table, it is available, I will access that page. So I will access from your cache, I given to this one, Now what I will do, when is miss occur, right, when miss occur access, that moment I can update what TLB, because future it should be it, right, I can update. Once after miss only, then I will update, before I may not do it. Update and given to this one, that is how I can do it. That is why when some gate question is being framed, they say page table updation and TLB updation time is negligible. They use these words, because when page fault occur, I will read a page and place it right and update all the things right. They say page table updation and TLB updation ignore, meaning you understand, when page miss occur, when you place it, I will update and restart the instruction. This will happen. Clear ma? So all of you, like what I discussed here, so try to watch from beginning so that you will get a proper understanding of the various topic from computer architecture ma. And similar way, even I discussed the operating system into 2 sessions were there, the quick revision or smart revision on operating system, that also is useful for last moment revision. I hope this session you might have enjoyed. So now we can stop the session ma. Yes, Somil, if you have any queries we can discuss, otherwise I am going to stop the session. Even further things, if you have any queries also, so you can visit, you can join this Telegram group, like you can say some free content, some free questions or some videos also you can get it. So you like this, that's better. Okay ma. So I will be going to stop the session. Thank you all, thank you so much for watching this session ma.